I don't know where everyone is. Just you guys online. I don't have anyone in the classroom.
Someone said on the WhatsApp chat, they asked if we even had class today. They said that maybe there's only classes until 6:30 or something today for some reason. I'll check the calendar.
Even with the student day, it's like my announcement says that classes are supposed to continue until 6:30. Not quite sure why people wouldn't show up, but
Yeah, it doesn't seem like there's anything on the calendar either. So
unless you guys know something online that I don't know. Okay, so let's get started. So last week we were, I take my mask off, there's no one here. Last week we were talking about separation. So we had discussed the idea of the location of the separation point. In fact, we learned that there were two different ways of identifying the location of the separation point with more and less accuracy. But we switched to a different question that we wanted to ask, which is, given that we can describe where the separation point occurs for a given body, can we modify where the separation occurs? Can we change the separation location? For instance, if we wanted to create a smaller wake behind the body to reduce the drag, could we move the separation point? Could we delay the separation, push the separation farther downstream? So that was the question. And we said that there are two basic physical processes that are involved in causing separation. And therefore, if you want to modify the separation, it's those same two physical processes that should be at hand, right? One of them is the advection of vorticity, that you get separation when you have an excess of vorticity being advected downstream. And the second problem is a lack of diffusion of vorticity, right? So if you have an excess of advection of vorticity downstream, that means that you're going to have too much vorticity versus the vortex sheet. And you're going to have to create a very strong vortex sheet at the wall in order to cancel this excess vorticity. And that vortex sheet, as it gets stronger and stronger, eventually that vortex sheet will cause a change in sign of vorticity, which is what causes the separation. The second process that can cause separation is having an inadequate amount of diffusion of vorticity. So given a vortex sheet of a particular strength, the question is, I want to prevent the vorticity from changing sign at the wall. I have all this negative vorticity in the bulk of the flow. How can I get that negative vorticity to come closer to the wall? And if I could drive that negative vorticity closer to the wall, then I could prevent the sign change in vorticity. So the two mechanisms for preventing a separation are to modify the advection of excess vorticity, or alternatively, to enhance the diffusion of the negative vorticity towards the wall. So we discussed a couple different techniques for doing each of these, right? The first and obvious one is that since we learned that you can identify the location of the separation point based on the shape of the object, obviously changing the shape of the object is the simplest way to change the advection of vorticity and to change the excess advection of vorticity. That's not the only thing you could do. You could also change the boundary conditions. You could change the wall velocity. If you change the wall velocity, you change the integral constraint on the vorticity, and that'll also affect how much excess vorticity there is. And you could imagine having rotating bodies. There are lots of different ways you could change the boundary conditions about the advection of vorticity. That was one option. And then the second option was, how do you enhance the diffusion of vorticity? Well, the simplest way is to transition to turbulence. If the flow is turbulent, you have much more mixing. You have a rapid mixing of vorticity from farther away from the wall towards the wall. That's going to be enhanced over the standard mixing due to diffusion. And that should help move some of that negative vorticity towards the wall to cancel the positive vortex sheet that's being created and to delay or eliminate separation. So that was one way. But there are other ways of drawing vorticity closer to the wall. And one that we saw earlier in the course was the idea of suction. You could apply suction at the wall. And if you can suck hard enough, you can bring that negative vorticity towards the wall. And you could even maintain the wall having a negative vorticity under all circumstances. You would never have any separation. But then we asked, well, how much suction is a lot of suction, right? How much do you actually need? It's one thing to say you need sort of an asymptotically large amount of suction such that there's no advection at all and you maintain negative vorticity at the wall, but maybe that's too much. So we actually used the Paulhausen technique and we said, how much suction would you have to add if you wanted to move the separation point to the downstream stagnation point, such that there was no separation at all on the surface of the body? And we did some approximations, but basically we showed that the amount of suction you would need to have relative to the free stream velocity should scale as 1 over the square root of Reynolds number. In other words, the amount of suction that you need to apply is exactly the same in magnitude as the velocity that's induced by the boundary layer pushing the streamlines away from the wall. In other words, you need to basically suck as hard as the boundary layer itself is moving away from the wall to prevent the boundary layer from moving away from the wall. And if you apply that level of suction, then the boundary layer doesn't actually grow as you go downstream. You maintain the same thickness of boundary layer, and the whole flow behaves as if it's a fully developed flow, as if there's no development in the X or in the theta direction. And if you do that, then in principle, you should be able to delay separation indefinitely, all the way to the stagnation point. So those are the techniques that we learned for controlling the separation points, moving it around, modifying the separation behavior. But everything that we talked about last time ultimately has to do with the assumption of a steady separation, right? We were assuming that these were all steady state problems, that you have a fixed separation point. There was no time evolution. And the problem is that in real separation, there's time dependence. But not only in real separations with time dependence, all of our discussion of separation never described how do you go from the unseparated state to the separated state, right? If you start with a flow that doesn't have any separation, and then at some point due to the pressure gradients, you have separation, what does it actually look like when you make that transition from the unseparated state to the separated state? So this was essentially the question that we ended with last time. And I said that we would do a little bit of discussion of this unsteady case, just because it's important in terms of understanding realistic separation behavior. And it also introduces a whole other area of ways of controlling the separation. Yeah.
Last lecture, you mentioned that during takeoff, there is a vortex which like detaches from the airport. Is this an example for an unsteady separation?
Sure. So that was, so there we basically saw that you have this, in order to get lift, that you have to have a vortex that separates. And when it separates asymmetrically, right? So the amount of vorticity that separates is of positive type or negative type is not balanced exactly. And therefore you end up having a net vorticity to the left that's bound to the wing. So yeah, we described that, but we didn't describe how it actually happens. I drew the picture, right? But I didn't actually say anything about how do you actually get to that state.
This is an example for an unsteady separation.
So that's definitely unsteady. It evolves in time. You know, the plane's sitting there and there's no flow, there's no vorticity, and then the plane starts moving. And when the plane moves, it generates a vortex sheet. We know that. We learned what happens. And then at some point, that vortex sheet gets shed through the separation process. And we saw that when it gets shed, because of the shape of the wing and the asymmetry of the wing, you're going to have an imbalance of vorticity that gets shed off the wing. But we didn't explain exactly how it is that the separation behavior actually occurs dynamically in time. We know what it looks like before separation, and we know what it looks like after separation. So we know what it has to be in these two steady states, but we didn't talk about dynamically what actually happens in between those two.
No over the cylinder, it's a steady separation.
Well, there's never really a steady separation. Meaning if you have a situation where you went from unseparated to separated in time, that's not steady, right? Now, does that unsteadiness continue in time? That's a separate question. But at the very least, you're going to have a transient, an unsteadiness for some instant in time, right? And that's what we're going to talk about. And then it could be that that unsteadiness persists and continues, right? And we'll see an example of that. Okay, so this is the question that we're trying to address. So in order to address this, we're going to deal with a very simple model problem. It's sort of a cute little model that was developed probably 30 or 40 years ago, which is not going to be quantitative, but it'll give us a qualitative feeling of what's going on in this unsteady process, and it'll help us to think more clearly about what's going on. And the model has basically two components. One, it has sort of a scenario, and then the second is how are we going to analyze that scenario? So the scenario that we're going to think about, you can think about it as the expansion in the flow inside a pipe, for instance, or a channel. Imagine that we have a channel that has a particular height to it. And then at some point, the height starts to suddenly increase, right? So you have a linear increase in height. And then you have a much larger channel downstream. So you could imagine this is a pipe going from a small diameter to a large diameter, right? So you could have it with two sides. I just drew it with one side. So one wall stays the same, the other expands. You could have both sides expand if you want. It doesn't really make a difference. Now, of course, what happens when you have this expansion is that the mean velocity in this region is high, and the mean velocity here, of course, is lower, and therefore the mean velocity is decelerating as we go through this expansion. So if the mean velocity of our flow is decelerating, so in this expansion region, we're going to have an adverse pressure gradient, right? The adverse pressure gradient means that we're going to have a vortex sheet that's created of the opposite sign. So we'll have a vortex sheet that's created right in this region. And if that vortex sheet is strong enough, then there's a possibility for flow reversal in that region, that the vorticity could change sign at some point. So I have that marked here. The vorticity changes sign. If the vorticity changes sign, therefore the flow reverses, therefore you have separation. But of course, downstream, you no longer have any positive vortex sheet. There's no longer a pressure gradient. So at some point, we expect it to reattach, right? So, and like we saw in 2 dimensions, you always have to have a reattachment point, you have a separation point. So here we have a reattachment point. And then downstream, the flow is perfectly attached. So in this region, this will be our separation bubble, okay? And again, if we think about it in terms of the vorticity profile, and in terms of this is the mean velocity. So the mean velocity obviously has a deceleration. You end up having a lower mean velocity on the wide, thick pipe versus the thin pipe. And if we look at our vorticity distribution, of course, we have all negative vorticity here in the profile near the wall. You can imagine that this upper wall is far away, right? So we're just really focused on this region near the wall, near the flat wall. This, by the way, is a nice way experimentally to produce a pressure gradient on a flat plate, right? If you wanted to produce a pressure, you want to study the flow on a flat plate. Why do you want to study the flow on a flat plate? It's much easier experimentally, right? It's much easier to make measurements if everything is nice and flat and smooth. But what if you want to produce a pressure gradient? And what if your pressure gradient you want to produce is some curved function? Well, you stick that on the upper flow. And whatever you stick on the upper flow, you'll get the mirror of it on the bottom flow. So you can actually create, of course, there's a separation bubble here also, right? I didn't draw it, but obviously you can have a separation bubble here, right? Just like you would for if you had some pipe that was separating, right? So you had your flow coming in like this, and of course you're going to have 2 separation bubbles right on either side of the pipe. So you'll have a separation bubble here also that mirrors this separation bubble. But if you do it if you set your experiment this way, this gives you a really nice way of making all your measurements on a nice flat wall. And especially if this had some sort of curved geometry, you wouldn't have to worry about any of that.
So do we assume the pressure is uniform in cross section on this? Or is it a 2-dimensional problem?
It is a 2-dimensional problem, but what's the boundary layer assumption here?
But we assume that the pressure is uniform throughout the pipe, the cross section of the pipe.
Well, all we're assuming is that there's a layer of fluid near the wall, right, about which we can assume the pressure gradient doesn't vary in Y. And this takes on whatever the irrotational flow is. So if you imagine in the center of this pipe some sort of irrotational flow, not near the walls themselves. So that irrotational flow is going to have some pressure gradient, which is going to vary only with X. not with y, right? Or at least the edge of that is going to mirror whatever's inside the boundary layer. So you have to be a little careful that if you had a very wide region of irrotational flow that had some pressure difference between the two sides, then it could be that you would have a different pressure gradient on top and the bottom. But you can design it so that they have exactly the same pressure gradient.
Why do you assume that the irrotational flow is only one dimension? It doesn't have a.
No, you'll have a two-dimensional one, but you can design your irrotational flow such that the bottom edge, if you imagine the irrotational flow is in the center, at the bottom edge of it, which is the top edge of the boundary layer here, you can imagine that that pressure gradient in X is the same as the pressure gradient on the top edge of it, which is the boundary layer for the top side. You can work it out. Anyways, it's not, the point of the problem is not to go into the details of how you actually construct it. It's just an interesting aside that lots of people who want to study separation bubbles, they don't want to study them in the actual environment. They study it in a mirrored sense. Our purpose really is to understand the dynamics of the separation bubble. That's what we're really interested in. So again, we have on the upstream side, lots of negative vorticity. And again, it's a high velocity. So the integral of all this vorticity is going to be a large number because that's the total amount of vorticity consumed here is the integral, essentially the difference between the wall velocity and the free stream. The free stream is higher here. On the downstream side, the free stream is now lower. So therefore, we're going to have less total vorticity. So you're going to have, if you compare these two, I tried to draw this so it looks like there's a less negative vorticity on the downstream side. And of course, where did the vorticity go? How did you decrease the amount of vorticity? You have too much that's being infected. You have this excess of vorticity that's being infected. So obviously a vortex sheet was created in this pressure gradient region. And the vortex sheet was strong enough that it actually created so much positive vorticity that it canceled negative vorticity, and we got a change in sign of the vorticity at the wall, which is what produced the separation bubble. Okay, so this is essentially the model that we're going to use to think about this. Where's my see the eraser on there? So this is the model that we're going to use, and we have to introduce some unsteadiness to this. So imagine that for time less than 0, we have just the straight channel, nothing interesting at all. And then imagine that for time greater than 0, we produce a channel that looks like this. And so you can imagine this either that we have a mechanical mechanism that we can all of a sudden change this wall. You press a switch and the wall changes shape very suddenly. So now we have this sudden pressure gradient that appears, or you don't even have to think about the wall at all. You could just imagine we have a magical pressure gradient that I can turn a switch and I can produce a pressure gradient that would correspond to this sort of deceleration of the flow. Doesn't really matter which way you think about it, but this is the process that we're going to think about. So we're going to consider this type of scenario where you produce over some finite distance, you produce an adverse pressure gradient, and then we're going to see how does this separation bubble actually form. So we go from a situation where there's no separation, we have a nice, favorable pressure gradient the whole way, this pipe flow, and then we have a region of adverse pressure gradients, which is going to produce a separation bubble. So how do we produce the separation bubble? So this is the first ingredient. The second ingredient is how we're going to model the flow on the inside. And the way we're going to model the flow is we're going to treat it as if it's an irrotational flow, and we're going to superimpose vortices on top of it. So we're going to pretend that the flow inside here is basically an irrotational flow. So that's just going to look like a plug flow. And then we're going to add to that irrotational flow a bunch of vortices. So imagine that here's the wall. We're going to add vortices. Now, how should we draw the vortices? Well, obviously, in the real flow, the gradient in the vorticity is strongest near the wall, right? So we should have the most intense vorticity near the wall and less intense vorticity away from the wall. And we know that the more intense vortices tend to be smaller, right? They tend to shrink up. You have intense vorticity in a small area. I'm actually going to draw it the opposite. I'm actually going to draw the bigger vorticity as larger vortices, right? So it's a little bit backwards from the perspective of thinking about the concentration of vorticity, but it'll make the visual picture a lot easier. So we'll assume that if there's a lot of vorticity at the wall, we'll put a big vortex there. And then as you move away, we have less vorticity. So we'll put a smaller vortex, and then a smaller vortex, and a smaller vortex. These will all be my vortices. And of course, if you superpose a bunch of these vortices together, then you're going to get a representation of a realistic flow, right? Where you have a lot of this reverse flow from the vorticity near the wall, right? And the vorticity gets weaker and weaker as you move away. So as you get out through the free stream, the irrotational flow, it looks like it's basically just the base irrotational flow, okay? So this is the model that we're going to use. And of course, there's a bit of a trick with this model in the sense that how do you get the wall if you want this sort of model to work? How do we enforce that there's a wall condition if you're taking an irrotational flow and you're adding vortices onto an irrotational flow? How do I make sure that there's no flow going through the wall, that I enforce a no penetration condition? This is something that maybe came up in your potential flow class. So what do you do to enforce?
Shikuf.
So you have a mirror, exactly. So you have to have an image. They call it the method of images, right? You have to have an image vortex. So this vortex here, you can see it's turning this way. So it would end up driving flow in the downward direction through the wall. So we need a vortex going in the opposite direction so that it'll drive flow in the upward direction, right? So we'll have another vortex of the same size in the upward direction, and then another one here, etc. Right? And if you do that, so now you'll have these two vortices, and you'll have velocities equal in opposite direction at the wall, so that the velocity of the wall is 0, and you have a no penetration condition. Yeah.
When you say that you add vortices, you mean like point vortex,
These are point vortices.
but it's irrotational.
Irrotational flow plus point vortices.
Yes, but the point vortices, they are
Right.
potential.
Right.
So the flow remains irrotational.
Yeah. It's an it'll look, the superposition of this flow is going to look artificially like a boundary layer flow, but technically it's an irrotational model, right? So it's a funny sort of model. It's an irrotational model of this process, right? But it's an irrotational model that has point vortices. So we're still dealing with what happens to vortices. We're just treating them not as a field, but as discrete units, right? And thinking about vortices as discrete units will actually be helpful in thinking about this unsteady process compared to thinking about the field. We already know how to describe the field in terms of its two different steady states, but here we're going to think about what happens to individual point vortices, okay? Now, when I put these other vortices on the other side of the wall, what happens? Well, not only does it give me my no penetration condition, but this vortex here induces a velocity. Every vortex induces a velocity, right? And we know that the vortex induces a velocity, and the velocity that's induced goes as 1 over the distance between the vortex and the point that you're inducing it. That's just the Biot-Savart law for a point vortex. So therefore, this vortex here is inducing a velocity. And remember, this, because I drew it as a big vortex, I mean it's a strong vortex, right? So this vortex here is going to induce a velocity at that point that's going to be going in that direction. And similarly, it's going to induce a velocity for this vortex. But of course, this vortex is farther away, so it's going to induce a smaller velocity. And then this one's also going to induce velocity at all these points. But the point is that this vortex is going to get a smaller velocity, and a smaller velocity, and a smaller velocity. Now you can see why I decided to draw bigger, stronger vortices as larger ones, because I want the arrow that's being induced to be longer. Otherwise, it gets a little confusing. So this vortex, the image vortex, which is only there artificially, it's just there for our no penetration condition, but it's going to induce a vortex velocity at these actual real vortices. Now, what do we end up seeing? Well, we end up seeing that these vortices are all being pushed backwards, right? So you have a background flow, and this background flow is going to advect the vortices forwards. But the image vortices are causing all of these vortices to be pushed backwards. the one that's closer to the wall is being pushed backwards the most because number one, it's closer to its image, and number two, it's a stronger vortex to begin with. The one that's farthest from the wall is going to be pushed backwards the least because it's farther, therefore the Biot-Savart radius is farther, plus the vortex itself that would be corresponding to it these are also smaller vortices. So you're going to end up producing a bunch of vortices that want to go backwards. The ones closer to the wall want to go backwards faster than the ones farther from the wall. And eventually you get vortices that don't really want to go backwards at all, and they just get ejected at the free stream velocity. Yeah.
What about the velocity, the vortices induced on cells? Like there is the most lower, the strongest one, and there is the one above it.
Yeah.
The strongest one induces a positive velocity on the one above it.
Yeah, absolutely.
So how can you tell that the vortex will move to the left if the strongest one induces a velocity to the right?
If the strongest one induces a velocity to the right.
Yes, to the second vortex from the wall.
But this one is also moving backwards, right?
Yes.
Right? And they're moving backwards at different speeds. This one's moving backwards much faster than this one is. So even though this one is, you're right, this one is also going to be inducing a velocity that's going to be pushing this one forward, but this one's moving backwards much faster. So you can get the balance right. You know, what are the exact numbers that you need to select? I don't know off the top of my head. You could do a little simulation in MATLAB if you wanted to work out what the numbers are such that you can get a balance right. So I don't have the numbers off the top of my head, but because these are moving backwards much faster, so the fact that this induces, you're right, that this induces a forward velocity on these also, it's not going to change the overall result. Right? You can still set it up so that the ones near the wall are moving backwards the fastest, and the ones that are farther away move slower and slower in terms of the backwards direction. Okay, so this is the basis of the model. Now all we have to do is draw the picture to figure out what happens when we introduce this model into this framework. So we're going to draw what it looks like at t less than 0, which of course is going to look just like this. And then we're going to consider what happens when we suddenly turn on the pressure gradient, the adverse pressure gradient. So let me draw this. So we'll try to draw it reasonably large. So we have our wall, and we'll draw a second wall at a time. So for our t less than 0, here we have our uniform velocity. And for the t less than 0, the uniform incoming velocity and the uniform outgoing velocity are the same. So nothing interesting happens basically in this case. Whereas, so this is the t less than 0. Whereas for the t greater than 0, so the incoming velocity is the same as above, but our outgoing velocity is going to be much less. Okay. And now I'm going to mark off the location of the adverse pressure gradient. Right, so this is going to be my adverse pressure gradient region. And now we have to draw in the vortices. So draw all these vortices in, and they're all negative vortices. One of them has its center, and like we said, because of the image vortices, they're all going to get pushed backwards with different velocities. Okay, so this is our t less than 0 case. So again, all this is just pure advection of vortices. Right? All of these vortices are just being advected by this uniform irrotational background flow. Each vortex is being moved downstream, but of course, the vortices here are being moved upstream by their image vortices. And now the question is, what's the net direction that the flow goes in? Well, as long as the velocity induced by the image, right? As long as that velocity is less, as long as this is less than this arrow here, and I tried to draw it so it's reasonably accurate. So as long as this then is less than that, so the difference between them will be the effective velocity profile we have here, right? So this will be the effective velocity profile of the vortices. If we were just watching what's the profile of all these discrete vortices, so the difference between the induced velocity this way at the vortex and the background velocity, that distance is going to be a little bit positive, and the vortex is going downstream. So as long as these vortices, as long as the advection of the flow is greater than the image advection in the opposite direction, then all this stuff gets advected downstream. Of course, the ones farther away from them will get advected faster, the ones closer to them will get advected slower, but everything is being advected downstream. As long as, again, these arrows in the negative direction are smaller than these arrows in the positive direction. Now, what happens when we, in this adverse pressure gradient region, we reduce the mean velocity, right? Meaning this velocity here is getting smaller, so that by the end, it's actually quite a bit smaller. So up here, there's no problem. There's no change at all. So I'll draw the same picture that I had before. So these are all fine. What happens to the vortices down here? Well, the upper vortices have no problem. These vortices have no problem. They're going to keep going downstream because this arrow, the velocity at which it's being advected upstream, is still smaller than the arrow that's advecting it downstream, even after the expansion. So these little vortices in the free stream are going to continue no matter what. Right? So I can draw them in all the locations because they're always going to go downstream. The problem is these bottom two, these much stronger vortices. Because down here, these two vortices, their arrows going in the opposite direction are bigger than the free streams advecting downstream. So they're actually going to reverse direction and they're going to start moving upstream. So the two vortices that were here, they're now going to start moving upstream because their net velocity is now going to be pointing in that direction. Their induced velocity is greater than the advection velocity. Now, how far upstream are they going to move? Well, they're going to move up until the point where the vorticity matches, where the reduced velocity matches whatever the local irrotational velocity is. So these vortices, as soon as we hit that switch and we turn that pressure gradient on, these vortices, which were moving happily downstream, are going to reverse direction and they're going to start moving upstream, and they're going to move up and they're going to move up and they're going to move up until at some point they stop. Right? So I'll draw their stopping location a little bit off, right? But here's their stopping location. Right? So they moved upstream to where their velocity matches whatever the velocity of the irrotational background flow is. Now the irrotational background flow is somewhere between this distance, then that's this arrow and that arrow, right? And I said it's going to sort of linearly change, but it's going to move up until the velocity just matches. Right? Now, when it just matches, now what happens? Well, that was these downstream vortices. What about the vortices that were already in this region? Well, if you reduce the free stream velocity here, these are also going to move up. So these vortices, just like the downstream ones are going to move up, these vortices are also going to move up. So they're going to move up too, and they're going to move up also exactly to the same location. So now we're actually going to have a second set of vortices here. Now, when these vortices move up, then they stop, right? Now we no longer have a movement of these vortices. The vortices have essentially stopped. The flow is essentially stopped in that location. And if the flow stops in that location, that's what you would call the separation location, right? That's the separation point. You have flow reversal, right? The flow here, downstream of this vortex, right? The flow is driving upstream, right? The induced flow of these vortices, they're all moving opposite the streamwise direction until the point where they stop. And these vortices are essentially being carried downstream. So you have these vortices that are all accumulated in this one location, right? Now, of course, there's only so many vortices that can come downstream, but you have more vortices upstream that are going to continue to come in, right? So you have more new vorticity coming in. You have whatever was downstream that moved up and joined the party here. And now what happens? Well, these vortices don't just sit there without interacting. These vortices can interact. Now, the whole problem of vortex interaction deserves an entire course, and there are whole books on it. We can't get into the details of it. But the point is, if we imagine these vortices sort of combining together, so you can imagine that these vortices are going to get stronger. So imagine that you have one vortex, which has a particular induced velocity, and now another vortex, just like it, joins it. They combine their circulations together. Now you have an even stronger vortex, right? That stronger vortex now has an even greater induced velocity now that they've combined. So as more and more vortices join this little party, it's going to start moving upstream further and further, right? Because with each new vortex entering the party, if you imagine that they combine, they have now a stronger induced vorticity. And that induced vorticity is going to be even stronger than the velocity. So it's going to head further and further upstream. Yeah.
Is there also a larger mirroring of the vortex?
Everything that happens here has to happen on the mirror side, yes, in order to enforce our no penetration condition. So we don't even have to think of it that way. If you want, you can just draw everything else. But everything that's happening on the upper side of the plate is happening on the bottom side. And that's why the induced velocity is getting stronger and stronger. Because every time I combine these two vortices, I combine their two mirror vortices, their image vortices, and it's sending it up further. So not only am I accumulating vorticity at a particular location where the flow is basically stopped, where the advection of vorticity has stopped, but these vortices tend to be moving upstream. At some point, they can't move upstream any further. Now, what happens when they can't move upstream any further? I mean that the vorticity has become so strong, that there's so much vorticity that's accumulated in this location, that the induction of the vorticity, the interactions between the vortices, cause some of that vorticity to be carried away by the separation streamline, right? We know that when you have this separation point, that you have a streamline which is going to be moving away from the wall. And it turns out that, again, if you go through the vortex dynamics, you can show that when these vortices combine and become much stronger, then eventually, after a certain buildup, some of this very, very strong vorticity is inevitably going to be carried away by that separation streamline. So what happens when you get a chunk of this vorticity, and all these vortices that were combined, they got stronger and stronger, they moved upstream, 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 and they got so strong, they got washed away. Now you're left with new fresh vorticity that comes in. Where does a new fresh vorticity go? Well, it goes downstream until it hits the zero position. And then more vorticity comes and hits it. And then the party starts again. They start joining together. And as it gets stronger and stronger, they start moving upstream. And then they move upstream far enough until they're so strong that they get washed away. And then the process repeats again. New vorticity comes in. The party starts downstream. As more people join the party, it gets stronger and stronger. It moves upstream until eventually the vortex is lost. It gets separated and it starts again. So what do we see in the process? We see an unsteady separation process that involves not a single fixed location of separation, but a dynamically changing location of separation. If the separation starts downstream, it moves upstream, moves upstream, moves upstream. When it gets to its most upstream position, a vortex is released, and then the separation line jumps back downstream, and then it starts building up vorticity again until it moves upstream. Another vortex is released, and then it goes downstream again. So if you're looking at this process from the perspective of our little separation bubble, I drew this as if it's a static thing, the separation bubble, but it's not. In reality, what you would see on this thing, and one of the classic ways of looking at this is the backward-facing step, right? What you would see with this backward-facing step, here you have your streamline that gets attached, and it reattaches. So here you have your flow that's reversed. Here you have the background flow. So what you would have is a process by which you start with a separation like this, and then this separation point moves forward. then it moves forward some more. And at this point, when it moves forward so much, the vorticity that's in here is so intense that you end up releasing a vortex, right? I'll just draw one of them. You release one vortex, and then after you release that vortex, you're back to the original location. So you have this cycle of a separation point that starts downstream, moves upstream even more, then you have a vortex release. And after the vortex release, then this thing is going to jump downstream, and then it repeats the process again, and it starts moving upstream. And you can see this, right? If you actually visualize the flow behind a step like this or an expansion of the pipe, this is exactly what you'll see. You'll see this separation bubble that's dynamically changing in time, has a particular frequency that's associated with it. Could be a very steady frequency, it depends on the outer flow. But you're going to see the separation bubble shrinking, releasing a vortex, getting larger. Shrinking, releasing a vortex, getting larger. Shrinking, releasing a vortex, getting larger. Yeah.
If it accumulate, if the total vorticity is constant, the amount of total vorticity in the boundary layer is constant.
That's what you mean. The outer vortices are still moving, right? It's only a localized accumulation. It's not a accumulation overall. It's a localized accumulation. And of course, as you locally accumulate vorticity, this is going to affect the flux of the vorticity above, right? So the total integral is going to be the same. But within that bubble, right? Within this bubble where the flow, here's the bubble is really right back here. This is the front edge of the bubble, right? But in the bubble, you have this reversed flow, right? And remember so as the flow is reversing, so the vorticity here is going to be getting stronger and stronger, but the overall amount of vorticity is the same.
So instead of having like a uniform or a very distributed vorticity, there is just a large concentration of negative vorticity in the
There's
water.
large concentration of negative vorticity of these negative vortices, right? I shouldn't say vorticity, these negative vortices that are being concentrated. And then at some point, you reach that limit, right? At some point, you gain so much that you reach that integral constraint limit. You can't put any more vorticity in this flow. And then that's when the vortices get released, right? So then they get sent downstream. And then once they get sent downstream, the process begins again. Then these new vortices can flow in. They go down to their equilibrium position. And then as more stuff adds to them, that equilibrium position starts shifting up and up and up until you accumulate so much that you get up to that integral constraint limit, release some of the vorticity, it's gone, and then new stuff can come in.
But what do you mean when the vorticity is released? Didn't we learn that the mechanism to solve this is to diffuse positive vorticity at the wall?
Again, this is an irrotational flow,
Ah,
right? So it's a model. So that's why I said at the very beginning, this is only a model, and it's not, just like all models, it's not perfect. So we're not treating this like it's a rotational flow, and therefore we're not going to be able to apply sort of the vorticity flux type arguments that we understood, but we are able to learn some interesting things from the model, right?
even though this is a model, vorticity does behave like this.
The model is very good in the sense that it enables us to understand why it is that when you look at the separation bubble, that it oscillates. Why does a separation bubble oscillate? So this model gives us a little bit of a picture. You know, if I was into the showing videos, you can find on YouTube, you can look at a separation bubble YouTube video, and you'll see this oscillation along with shedding. So you'll have the separation bubble oscillates, sheds a vortex, oscillates, it sheds a vortex. So this model is designed to help us understand that in terms of a very simple advection of vorticity, right? That's all it is. It doesn't capture, of course, the rotational field perspective of vorticity. But for that, we can just solve the equations. I mean,
There is no diffusion in this model.
no diffusion, right? This is a purely irrotational flow where we've added point vortices.
The mechanism of vortex release, or we just
No.
the general idea?
No, this is it. Just a way of thinking about it. So the take-home message from the analysis is that you can sometimes use a sort of irrotational discrete vortex model to explain complicated things like a dynamical problem. So for the non-dynamical problem, so we were able to explain everything in terms of vortex fluxes. But as soon as you add the time dimension, it becomes much more complicated, right? Because now you're trying to essentially describe a PDE instead of a nice ODE, right? Once we add the time dimension. Now it becomes a much more difficult problem to describe what's going on. But this is where a reduced order model can help you. So sometimes modeling the flow as just a superposition of point forces can help us give us some insight into what's going on. And then once we have this insight, then we could say, well, how is this useful? Well, now we know that the process of separation has some unsteadiness built into it, according to this model. Maybe we can use that to our advantage. And maybe we don't have to create this artificial pressure gradient where I turn it on with a switch. Maybe we could imagine creating something that allows me to have a dynamic, constant, periodic effect on the flow. Meaning maybe we could create a wall, but in the wall, we'll put a little hole in the wall, and we could have a little stopper. And this stopper could move, could oscillate it up and down, so that this little position in its up position could block the flow, right? And then, of course, it would oscillate between the down position and the up position. So you can imagine a little fence like this that you build into the wall. Now, what can this fence do? Well, imagine what happens when this fence is up. It has a couple different effects on the flow. One is it creates a blockage of the flow. So it's going to slow down the irrotational aspect of the flow, just like our expansion here slowed down the irrotational flow. So as soon as you slow down the irrotational flow, you're going to create an adverse pressure gradient behind it, which is going to create a separation bubble. So now you have a separation bubble that you create downstream of it. Secondly, it's going to deflect the vorticity over the flow. So not only does it create this pressure gradient, but you can imagine that the vortices that are coming down are being deflected over the flow, and they're also going to induce velocity changes in the vorticity downstream. Furthermore, on the top edge of this little, imagine this is just a little fence piece, you have a pressure gradient itself on the top edge. So you're going to have a shear layer of vorticity from the top edge itself that's being released. So you're going to have vorticity that's released due to the pressure gradient on the top edge. You're going to have some separation region downstream where the flow is being reversed. This thing, of course, could be moving, right? According to our model, this is going to move upstream. But the interesting thing about this moving piece is that I could imagine, unlike the case of my expansion in the pipe, this time I could imagine maybe I'll move my little fence piece at the same sort of frequencies that I know the shedding is occurring at, right? Meaning maybe I can tune this sort of fence piece to match the types of shedding frequencies that are going on in the problem. In other words, maybe I could actually create artificial blockages, right, with the right frequencies that could affect a larger separation problem. So if I have a flow problem like here, where I know that I'm producing a separation bubble and this is moving up and down with a particular frequency, I could imagine putting some little fence here on the top. And I can imagine tuning that fence to the right frequency to try to interrupt the process of vorticity transport in this downstream region. Now, it's a very complicated, process of what's going on here, and we devote whole lectures to flow control and how do you actually choose these frequencies, what are the right frequencies to do, and what's the effect. But all I want to point out now is that once you know, according to our model, that there is a certain frequency, a certain periodicity to the separation bubble, once you know that, now you immediately think, well, maybe I can use that periodicity to my advantage. Maybe I could put some sort of actuator that has a similar frequency. And it doesn't have to be a metal fence like I'm describing. You could put a little plasma actuator. You could put a little jet. You could put a little suction thing there. You could imagine having a suction on the upper edge here, and you only have to apply that suction at the frequency that the vorticity is actually being moved up and down. So maybe you want to prevent the separation from being unsteady. right? Maybe you want to cancel out the unsteadiness. Now, why would you want to cancel out the unsteadiness? Well, you could imagine that the unsteadiness is very inconvenient if you're trying to design a wing that has a very constant load of forcing on it, right? You have this wing and it's designed to behave very nicely, but it has this periodic change in the forcing. And you have no way of controlling that periodic change in the forcing because that's just the nature. There's a separation at some point on the wing, and the separation is essentially unsteady. This is what they call dynamic stall, right? What's the word dynamic there for? It's that the things are changing in time. So how can you adjust that? Well, you could imagine putting some sort of fence, putting some sort of actuator in there, and tuning that actuator to the same frequency to try to prevent the vortex shedding. Maybe you add some vorticity of the opposite sign into this collection, or maybe you cancel the vorticity that's building up, or maybe you add enough additional free stream momentum into the problem to wash the vorticity away before it can build up, right? So you can imagine any number of these techniques. And the point of this whole little toy problem is just a way of thinking about these. So the next time you see an example of a jet actuator or a plasma actuator on a wing that's being used for separation control, and they tell you that they're actuating this actuator at a particular frequency, why are they actuating at a particular frequency? This is why. They're actuating that actuator at a particular frequency because they're trying to cancel out the inherent natural unsteadiness in the separation process. Okay, that's everything that I want to say about separation. So I think we'll take our break here, and then we'll talk about instability.
Reason you can say that the flow stalls because the vorticity is accumulating is because of Helmholtz argument, vorticity travels with the flow.
There's no diffusion. Yeah. If there's diffusion, this doesn't work, right? If there's diffusion, then the vorticity does not necessarily travel the flow, these can spread out. So it's not purely advection. This whole model assumes pure advection.
So
Right.
Helmholtz argument that vorticity is travel with the flow.
That's only true when you ignore diffusion. Right? I mean, that the Helmholtz rule that you're referring to, normally they just drop off the term that has the viscosity, right?
But Helmholtz
if you-
proved it in a general way because there is like a vortex tube and it looks like a material.
Right, but you look in the notes from, I don't know, the first or second lecture, and you'll see that's in the Kelvin-Helmholtz theorem, that there's a diffusion term.
So there's a
Right? So if there's a diffusion term, so then it's not pure advection. So a vortex that starts here doesn't necessarily have to end up where the streamline takes it, because between here and here, it could have spread out a bit. It could have diffused to other locations away from that streamline.
So now there are two fields, vorticity field and like velocity field.
Well, the point is that the vorticity can diffuse. It's not stuck to being fixed on the streamline, that it can diffuse away. However, if you assume the Reynolds number is large enough and the diffusion is relatively weak, so then this sort of model can be helpful. It's not going to be perfect. And this model is never going to explain what's going on exactly at the wall, because of course it doesn't get the vorticity fluxes. And there are certain features that it just can't capture. But as a general picture, if you assume that the advection is the dominant effect, then that's what this model does. This is an advection-based model.
I had some trouble in the problem set, like understanding what a vortex shift actually is. Like there are two ways to calculate it. One is like the difference between the potential flow and the flow on the surface.
Right.
And the second method is like to integrate the
They're the same.
circulation. Yes, but what is the actual definition? How do you define vortex sheet strength? Which of these two options is the actual definition?
Vortex sheet strength is a circulation per unit length.
This is the dominant. Okay. Like you can
So-
calculate circulation,
But the circulation is, like I said, what the two things you said are exactly the same. They're just ways of calculating circulation.
Yeah, like you can define circulation as the vorticity flux, or you can define circulation as an integration of the velocity on a closed curve. But
No,
the
the
second
the
one-
definition of circulation is always the same. It's always the integral of vorticity. The outer plane vorticity. That's the circulation. That's the definition of the circulation. And therefore, if you're doing it circulation per unit length, which is little gamma, so usually the unit length happens to be the x direction. Doesn't matter, but that would just be omega z dy. That would be,
if I'm working in polar coordinates.
so then you just write whatever the polar definition is.
Like I had a problem,
So the polar definition, I don't know, you tell me what it is. Something like that. Right?
circulation per unit length, now you don't have like another length dimension, don't have dy, you need to differentiate according to something
R.
else.
R direction.
So you integrate in the R direction. And the integration is in the R direction, but the differentiation of circulation is in one direction.
I don't understand. We're talking about this vortex tube, right? Which has Z direction, the R direction, and then you have this is the theta direction, right? So in this case, you have your vorticity is the theta direction, right? So if we were to define, our volume, right? So this would be the Z R integral, and the vorticity is into the plane or out of the plane, right? So total circulation would be an integral over of this vorticity R dz, right? That's the area. And then circulation per unit length would be in the z. We'll take the length of the thing in the z direction. That's just going to be omega r, right? And then this comes out to be, I don't know what it comes out to. It's something uz dr with a minus or a plus, something like that. I don't remember what it is. Something like that. So then you plug it in, and you end up getting dz, dr, and then it's exactly the same as what you said, just a difference in the velocities.
I had a trouble like determining the sign of the strength of the vorticity.
Okay, well, it probably doesn't matter, except that you can figure out which direction it's going to be inducing the velocity.
Yeah, I got the just induced into the tube, but not out of it.
Right, so just figure out which way that it makes sense for it to go. You know which way the ring is going, so you can figure out in what sense the vorticity has to be generated.
It must be negative. I just like I did the integration.
Yeah.
From the
You can also think about it. If you think about, this is, I don't know, these are the lips of a person's mouth, right? And you have your velocity profile coming out. So which direction are your vortices going to be going, right? When it comes out, right? There's going to be this big pressure gradient right on this corner here of the ends of the lips, and that's going to produce these vortices. And then, given which way the vortices are, you can figure out which sign the vorticity has to be. So you can work it out. If you just draw the picture and think about how it's generated at the end of the tube, the end of the mouth, figure out what's the sense of the vorticity.
but
So
I
you can
want
work it out. What?
I want to calculate like which the sign.
Yeah, I think, but the sign comes from the picture. Right?
Not from the integral.
No, the sign comes from the picture. You have to know what sense of vorticity is being generated when this plug flow gets to the end of the mouth, right? It's perfectly happy in the mouth, and then it comes to the end of the mouth, and now it has this sudden change in shape, right? Which is what the corner is. That sudden change of shape is a pressure. That's where the vortex sheet is actually being created. There was no vortex sheet before.
So there isn't.
So the vortex sheet is being created at the edge, just like at the leading edge, right? We have this vortex sheet that's being created,
There isn't a vortex sheet on the cylinder itself.
not until it comes out the mouth,
Ah,
right? As it emerges, it's getting a vortex sheet, right, which is being produced by the pressure gradient at the edge. So when it comes out, that's where the pressure gradient produces the vortex sheet. And from the picture, you can figure out. Now, of course, you can figure out from the pressure gradient also. If you want to do it all the math, you can figure out, well, what's the sign of the pressure gradient, right? That here we have, or what's the sign of the deceleration of the flow? And if it's decelerated here, what's the vorticity that's being created? What's the vortex sheet on this corner? What's the vortex sheet on that corner? You can work it out all, but it's easier just to draw a picture.
but the piston starts to move like instantaneously.
Right. So we're just pretending that we don't have to worry about all the details. So we,
Doesn't this create the vortex sheet inside the piston? Starts to move.
sure. So again, the different ways of thinking about it, right? If you want to think about it as the instantaneous startup, that's one way of thinking about it, right? And you can work out the vortex sheet through an instantaneous
So
piston
I
sheet.
can't get the right sign.
I think it should work out, but if you want to get the right sign that's in a physical system, so then this is the way to think about it. Think
The
about
sign depends on the direction of integration. If I
No.
integrate,
it doesn't depend on the direction. The vorticity will be opposite on the two sides, but it's one vortex, right? Because the vorticity is in the sheet, right? Is into the plane, into the board, right? So if I draw one vortex ring, I don't know, how for me to draw it, right? So one vortex ring that it has a particular sense here, be tough to draw, but as it comes around, it's going to look like it's the opposite. It's going to look like it's the opposite sign on the other end.
but there is a difference if you integrate from the center of the tube to the wall or from the wall to the center of the tube.
It's not gonna come out any different. I mean, if you obviously there's a sign in the integral. If you
Yes.
flip the two, you'll get different
Yes.
integrals, but that's not going to change anything.
אז השינוי סימן בגלל הכיוון של האינטגרל.
If you go from 0 to infinity, that's equal to the negative of the integral from infinity to 0, right?
אז זהו, אני לא עשיתי מאפס לאינסוף, עשיתי...
Well, from whatever, from A or R, whatever it is to infinity.
זהו, עשיתי מ-R ל-R.
But it's the same thing. That if you switch the limits of the integral, the sign of the integral changes.
עכשיו, האינפיניטי פה, זה לא באמת אינפיניטי של שכבת גבול.
Right. Exactly.
סוף שכבת הגבול.
It doesn't change because the flow is 0 everywhere outside it anyway. Right? You only have two velocities if you assume that it's a plug, right? You have the velocity in the plug and the velocity out of the plug. So it really doesn't matter what limits you take, as long as one limit is somewhere in the plug and or the surface of the plug and the other is outside the plug. It doesn't matter what positions you choose exactly.
כשאמרת בתרגיל הבית לחשב מאפס לאינסוף.
Right. But really you have to go from 0 or you have to go from
the wall.
You have to go from the edge of this thing
Yes.
here to there. That's all you need, right? Because here that's where the jump in velocity
אז אני
is.
עשיתי אבל הפוך.
Doesn't matter. Makes no difference. It'll come out the same. You do it the opposite, you have a sign minus in the integral, but it's going to be the same value, right? But it doesn't matter. So if you instead you go from here to there or here to here, it's all the same because the velocity in here is u, the velocity here is u, the velocity there is 0, the velocity there is 0. So it makes no difference whether you define it from this here to here, there to there, here to there, there to there. It's going to give you the exact same value.
כשאני עושה את האינטגרציה, יש את האיבר הזה בקרל, יש את האיבר שאני גוזר את המהירות ב-Q,
Yeah.
לפי את המהירות בכיוון R, אני גוזר אותה לפי Z. אני צריך להסביר למה אני יכול להזניח את זה?
No, the Z, again, there's no variation in Z in the plug flow. It's a plug, so there's no variation in the velocity in Z.
אני מחשב את ה-circulation per unit length.
No, but there's no variation in the Z. When you do this calculation, just like in all of our calculations in the boundary layer, we never took the X variation into account. Doesn't make a difference.
פשוט הראינו את זה עבור boundary layer.
From the irrotational flow perspective, there's no difference.
אז אני לא צריך להראות למה אני מזניח.
Okay, fine. So let's continue. Now we want to talk about instability. Okay, so we mentioned in terms of flow control that one of the ways of modifying the separation location is to induce a transition to turbulence. And we know that turbulent flows do a better job of mixing. They can mix the negative vorticity in the bulk towards the wall, and therefore reduce the chance that you're going to have a sign change in the vorticity at the wall. So therefore, obviously, the turbulent boundary layer is a very important thing to examine. And we'll spend basically the rest of the course now trying to understand the turbulent boundary layer, whereas up until now, we've just studied the laminar boundary layer. And the first thing to talk about in terms of the turbulent boundary layer is how do you get to a turbulent boundary layer? How do you go from the well-behaved, nice laminar boundary layers that we've been talking about to a case of a turbulent boundary layer? And we're going to study this. And someone asked last time, well, isn't this the same sort of thing that we study in instability class? And the answer is yes and no, that our perspective is going to be a little different. We're going to solve a problem that's different from what you solved in the instability class. But moreover, we're going to emphasize physical understanding. The class on instability is basically a math class, pure math class, right? There's a mathematical technique for studying instability. You learn how to apply that technique. And we're going to do a little bit of that, but we're really interested in understanding transition to turbulence and the stability of a boundary layer or a wall-bounded flow. But we want to understand it physically, and specifically, we want to understand it with respect to vorticity dynamics. That's been our tool for understanding all of boundary layers. So that's the basic idea. Now, in order to do this, of course, we need to think about what causes a flow to be unstable. And hopefully, most of you have at least a little bit of familiarity with the idea of turbulence, but we know that turbulent flows they look somewhat chaotic. They look like they're made up of lots of perturbations. And therefore, when we think about the transition to turbulence or a flow that's unstable, we usually think about the idea of a small perturbation to the flow and whether that small perturbation to the flow tends to grow or decay. And we know that that small perturbation to a flow, if we imagine we take a little chunk of fluid and we add a little vorticity to it, or we take a little vorticity away from it. So now it's perturbed from its equilibrium state. And the question is, does that perturbation grow and get worse and cause the whole flow to become unstable, like any mechanical system, that you push it out of equilibrium and it goes crazy? Or does the mechanical system go back to the way it was? You push it a little bit and it returns to its equilibrium. So that's the basic problem of stability for flows, just like it is for stability in mechanical systems. Now, the question in flows is, what are the forces that could either make it worse or better, right? What could drive it towards stability or away from stability? So we know that the diffusion of vorticity would tend to even out gradients, just like diffusion always evens out gradients. So if you have a small little perturbation of vorticity, we would expect diffusion to even out that perturbation and return stability to the flow. Whereas advection is just going to take that perturbation and move it along without giving it a chance to get smoothed out. And therefore, we would expect that advection is going to make the situation worse. It's going to prevent a flow from stabilizing itself. So if we want to think about the stability of a flow, we should really think about the ratio of the advection to the diffusion of vorticity. And we can take a particular example of this. If we think about our friend at the cylinder, so we have our flow around the cylinder, and I'll draw the flow in the cylinder. So there's our boundary layer growing, and then we have some separation. Right? And the separation is whatever it is, 100, 110 degrees, somewhere around there. And then, of course, here we have our boundary layer thickness. This is delta. We have a cylinder of size A. And we can ask ourselves, when we look at this flow, we have a boundary layer region, right? And then we have our boundary layer region, and we also have a wake region. And we can ask ourselves, which of these two regions is more or less stable? Meaning, which of them is more stable to a small perturbation in vorticity, which is less stable? If I know what the vorticity distribution is in a perfectly steady state, we can calculate that. We learned how to do it. If I were to take that base vorticity distribution, and I would take a little point here in the boundary layer and change the vorticity, or a little point in the wake and change the vorticity, which region is going to stay more stable or less stable to that small change in the vorticity? Well, I just said that the way to analyze this is to think about the ratio of the advection of vorticity to the diffusion of vorticity, right? So the diffusion or the diffusive flux of vorticity, well, we can write that as our diffusivity, nu, times omega over delta, right? That'll be the diffusive flux of vorticity in the boundary layer. We assume there's a certain amount of vorticity in the boundary layer. This is just a characteristic analysis, right? Characteristic amount of vorticity omega over a length scale delta. That's like our vorticity gradient. So this is our vorticity flux, diffusive flux. And then, of course, we have the advective flux. The advective flux of vorticity. Well, the advective flux of vorticity, this is going to be our free stream velocity, capital U. So the advective flux of vorticity is just going to be U times omega, right? This is all in the boundary layer. So therefore, the ratio of our advective flux to our diffusive flux, right? So this is our advective flux to our diffusive flux. Well, this, of course, is equal to U delta over nu, which is RE delta, which is the Reynolds number. What?
So when we talked about the nu Fuentes Blasius solution, we already did this. We found this ratio.
Yeah. Everything's always the Reynolds number, right? So therefore, this is the number that's going to tell you how stable or unstable the boundary layer region should be, right? So if the Reynolds number based on the boundary layer is very large, the advection is dominant over the diffusion, so we would expect the boundary layer to be less stable, right? And as the Reynolds number based on the boundary layer is smaller, that means the diffusion becomes more dominant, and then we would think that the boundary layer becomes more stable. And we could do the exact same analysis for the wake, right? That we have the exact same analysis for the wake, and if you do the analysis, well, for the wake, well, what's the characteristic length scale in the wake? Well, the characteristic length scale in the wake is the same length scale, right? It's A. So in the wake, of course, we have nu, but now it's omega over A. And here we have U times omega. And therefore, in the wake, we're going to have UA over nu, which is REA.
What kind of diffusion do you have in the wake?
The same natural diffusivity that you have due to the diffusivity of momentum and vorticity in any flow.
But now we don't have a wall.
Doesn't matter. You don't need a wall for diffusion. Remember, it's a physical property of the fluid. That's why we said that we never ignore viscosity, right? Because viscosity is not an assumption. Viscosity is a material property. Depending on what fluid you have a particular viscosity. And the kinematic viscosity, the viscosity divided by the density, that is an equivalent of a diffusivity. It's a momentum diffusivity. And we argue that we can treat it sort of like a vorticity diffusivity also, even though it's not exactly.
So there is like the rightmost element in the vorticity dynamics.
Of course, always, all these terms, right? They're always there. That was the whole point of the asymptotic analysis. All these terms are always there. It's just different levels of approximation, right? But all the terms are always essentially there. So therefore, we make the exact same argument by the wake, that if the wake Reynolds number is very big, then we expect the wake to be not very stable. And if the wake Reynolds number is very small, then the wake becomes more stable. And now we want to answer the question, well, which of the two is more or less stable? Well, we need to be able to compare the two. In other words, the difference, the ratio of these two is, of course, related to the ratio of A and delta, right? So RE delta over REA, well, that's equal to delta over A. Well, what's the ratio of the thickness of the boundary layer to the thickness, which is the characteristic length scale of the body?
This was a parameter when we did the approximation, the asymptotic approximation.
Yeah. And what is it?
זה היה פרופורציוני, גם כן משהו, אחת שורש ריינולדס, אבל לא זוכר ריינולדס של מה.
Reynolds A. Right? So this is what we learned from our asymptotic analysis. And the truth is, this is what we learned from the second lecture before we even did the asymptotic analysis. Just by doing a dimensional analysis of the equation, we actually got this relationship. We used L back then, right, instead of A, but it's the same thing, whatever the large scale characteristic length scale is. So if that's the case, well, therefore we know that RE delta is therefore 1 over square root REA times REA. In other words, RE delta is always asymptotically smaller than REA, right, by this factor. So the Reynolds, so whatever our flow conditions are, the Reynolds number in the boundary layer is always going to be much, much smaller than the Reynolds number in the wake. So therefore, where do we expect to see instability first? Well, we expect to see instability in the region that has the largest effective Reynolds number. So for one set of flow conditions, the effective Reynolds number in the wake is going to be much, much larger by a factor of square root REA than the Reynolds number based on the momentum thickness, right? Based on the boundary layer thickness. So therefore, we would expect to see instability appear in the wake first. Right? And in fact, this is what you see, that if you take a look at imagery of the flow over a cylinder, you're going to notice as you increase the flow velocity and therefore increase the Reynolds number, you're going to notice instabilities. The wake is going to start looking sort of random and chaotic and turbulent long before the boundary layer itself. The boundary layer can look nice and smooth while the wake looks very chaotic, right? Precisely because it's the wake region that has the higher effective Reynolds number, and therefore the wake region is the region where the advection is the dominant effect. Okay. The point of saying all this is essentially to emphasize that if we're talking about the stability, the worst case scenario for an unstable flow is an unstable flow where the advection is dominant, right? Meaning if we're trying to look for flows that are unstable, and that's what we want to focus on, we really don't have to worry about the diffusion. We should really just focus on the advection, because according to what we said here, the diffusion is always going to work towards stability. And if we're trying to understand when flows become unstable, so let's just forget about the diffusion altogether and focus on flows where there's just advection, right? And this is basically the approach that we're going to take, and it's the approach that all of the early investigators took when they studied the stability. So we're going to eliminate all the diffusive terms from our equations, and we're going to consider what happens when you put a small perturbation into a flow, but we assume that there's no diffusion in the flow. So we're taking the worst possible scenario. We put the perturbation into the flow, and we consider just the advective effects of that perturbation. Okay?
Is this the equivalent of
the flows
in
that
this?
we're going to consider are still rotational flows. So I'm going to write the equations of motion, right? But there aren't going to be any of the diffusive viscous terms. But again, we're not assuming the flow is irrotational. The flow is still rotational, right? It's just rotational without diffusion. So the rotational flow that we're essentially talking about is a type of flow where you have vorticity in the flow potentially. But we don't know we don't know where it came from, because without the diffusive terms, we have no way of talking about a vorticity flux. We have no way of describing where the vorticity came from. But we're assuming that there could be vorticity in the flow, but it's just being advected along. Right? It's just purely advected, sort of like the model that we used before, right? Where we just imagine that there are these vortices. There was point vortices. Here we're going to talk about a vortex field, but we assume that there are vortices that are just being advected along. So too here, we're going to assume that you have a rotational flow, but there's no diffusion, because we want to choose the absolute worst possible case. We're going to put a little perturbation into that flow. We're going to get rid of all the diffusive terms. We're going to assume the perturbation is so small that we can actually linearize our equations. We'll see in a second. And then we'll ask the question of, does this little perturbation grow or decay? If the perturbation grows in time, if it gets bigger and bigger, then we assume the flow is unstable, right? It's like when you push the mechanical pendulum and it goes all out of control, right? Because the little small push that you gave it initially gets worse and worse. Whereas if the system were stable, if the pendulum was right side up, so to speak, and you gave it a little push, it'll return to its equilibrium. So the whole question that we're going to ask is, in a flow where there's purely advection, and you put a small perturbation in, what happens to the perturbation? Does it grow or does it decay? And under what circumstances?
How do we define flow stability? Like if we refer to the pendulum example, we demand that the first derivative will be negative, and then I know there is stability. But in flow, how would
There's only really one definition, and the truth is that that definition is the same for the pendulum also, and that's a small perturbation. Does it grow or decay? So if you imagine your case of your pendulum, and you describe the position of the pendulum, right? So we have a variable that describes the position of the pendulum. Replace that variable with an equilibrium position plus a small change to that position, right? And now the question is, that small change, does it grow or decay in time? That's the only question that you analyze. So when you're analyzing the pendulum, you actually do the exact same process that we're going to do here. You add a small perturbation to its position, and then you ask, does that small perturbation go to zero? And as the pendulum returns to its equilibrium, or does that perturbation get bigger and bigger as the pendulum moves far away from its equilibrium? That's what we're going to ask. And we're going to do it in a problem, in a geometry that we've already seen before, which is the geometry of a wall with some curvature to it, just to make life interesting. So we'll have a radius of curvature r, right? And we're again going to assume that we have some local Cartesian coordinate system, x and y. So therefore, there's going to be some curvature, but it's not going to be very strong curvature. Right? So the curvature will be weak enough that I can locally describe the flow using a Cartesian coordinate system. And therefore, we're going to do the exact same procedure we did back when we first introduced this analysis with the polar coordinates. We're going to write the momentum equations in polar coordinates, and then we're going to replace all of our terms so that y is going to be r minus capital R, and x is going to be theta times r, right? And we're going to use this sort of quasi-Cartesian approximation. We're going to plug that into our polar coordinates equations, and we're going to write quasi-Cartesian equations to describe the momentum on top of this surface. And again, we're not going to include any diffusive terms. So I'm going to skip some of the equations just because it's a lot of writing. So I'm going to skip just after we rewrite our equations in xy form. So we have u dt plus b u dy plus u r y plus r x plus u v y plus r, and then we have the pressure gradient r over y plus r p dx. And again, no diffusive terms because we're assuming worst case scenario. We have a y momentum equation. And again, we're not using any other approximations in our analysis here. Y u r y plus r x u squared y plus r, pressure gradient in the y direction. And of course, we have the continuity equation, d dy, d over y plus r over y plus r du x equals 0. Okay. So these are the governing equations. So no boundary layer approximation. Full momentum equation, except that we're excluding the diffusive terms, but we're not assuming that this is rotation. So here it's possible that this flow is rotational. In fact, we will assume it's definitely rotational flow, but just no diffusion of momentum, no diffusion of vorticity. X momentum, Y momentum, continuity equation. Now, as we did before, we always want to reduce this down to one equation instead of two. So we use the fact that the flow is incompressible. Therefore, you can use a stream function. So we can write our u as psi y, and our v is negative r over y plus r psi x. And we're going to define the Laplacian, which is actually quite complicated. So it becomes r squared over y plus r quantity squared dx squared plus b squared y squared plus 1 over y plus r y. So our Laplacian operator. In other words, this is this thing. And so using this, we can of course rewrite these equations. So I can substitute in my u and v in these two momentum equations. And I'll get two momentum equations that are in terms of psi, but I still have the p dependence. I want to get rid of the pressure gradient terms. So I'll differentiate my x momentum equation by y. I'll differentiate my y momentum equation by x. Now I'll have a d squared p dxy and d squared p dxy in both of these. Then I can simply subtract the two and cancel out the dp dx and dp dy terms, get rid of the pressure terms, and then I'll have a governing equation that's an equation that's only a function of psi. Okay? So when I do all that, I will get an equation in psi. So you convert all of that into an equation in psi of xy only. And then I said that we want to assume there's a small perturbation, right? So the solution to our equation psi, we're going to assume that there's a solution to this equation that's a background flow plus a very small perturbation. In other words, we can write that our psi xy is going to be equal to some psi 0 xy or some psi 0 y. I'll assume that my background flow, the base solution to this flow, is going to be a velocity profile that doesn't vary with x, it just varies in y, right? So this is what you would call quasi-parallel or fully developed, whatever assumption you want to call it, or fully developed. So we're going to assume that the base solution to this profile is just going to be something which depends only on y. And in addition to that, we're going to assume, so this would be relevant for a channel flow, for instance. Imagine that this is a channel flow, a slightly curving channel. So you could put the top on this also. So this is a channel flow just with a slight bit of curvature to it. This could be, so example here would be a channel flow. So our base flow depends only on y, but then we have a small perturbation. Well, if we have a small perturbation, let's use the notation that we learned from asymptotic analysis. And let's call it epsilon times sin y1, where y1, of course, will depend on everything, x, y, and t. This is going to be our perturbation. Therefore, sin 1 itself is now order 1. We put the one epsilon in front of it to show that this quantity is small in comparison to the base flow. Right? Well, now I can substitute this definition of psi into the equation for psi that I already got from my momentum equation, and then I can linearize it. So step one was we developed the equation for psi. Step two was we made this a definition for psi in terms of a base flow and a perturbation, right? So this is the base, this is the perturbation. And then step three, we're going to substitute this into 1 and then linearize with respect to epsilon. In other words, we're going to drop all the terms that have epsilon squared. So we'll just consider terms that only have order epsilon. So these are the 3 steps. And again, it's just a lot of math, so I'm not going to write it all on the board. But what we get is a linearized equation for psi, linear with respect to the small perturbation. And then what we want to do is we want to study the small perturbation. That's what we're really interested in, right? So the final thing that we have to do is after we linearize it with respect to epsilon, is then we're going to write order epsilon equation, right? Because we don't care about the base flow. We don't care about this solution. It doesn't really matter if this is a channel flow. We don't really care what the base velocity profile looks like. All we care about is psi 1. Psi 1 is our perturbation, and it varies with time. Is it getting bigger with time, like our pendulum that was upside down and now it's swinging all the way around? Or is it like our pendulum that was right side up and it's just oscillating and then decaying? So all we really want to know is the psi 1. So our final step is we're going to write just the order epsilon equation. The order epsilon equation is the equation that governs psi 1. So let me write down that equation. So our order epsilon equation is r plus y over r ddt of Laplacian psi 1 plus, now in order to do this, we just need to define, I'm going to define my outer flow u of y as d psi naught dy. So I'm just going to define base flow. Just so that we have some notation. If you want, you could call this u naught, right? But whatever the velocity field that corresponded to my quasi-parallel flow assumption, we're going to define that. And that way I can use the notation, just so I don't have to just write d psi naught dy. This makes all the notation much easier. So this is times u ddx of the Laplacian of y minus d psi 1 dx times u double prime u prime over y plus r minus u over y plus r squared, r squared equals 0. So this is the result of these 4 steps. We wrote our momentum equation in terms of the stream function. We wrote the stream function in terms of a base flow, u of y, and a small perturbation, psi 1. We substituted the psi definition into our governing equation for psi. We linearized, and then we wrote the equation with respect to epsilon only, neglecting all the epsilon squared terms, and we got this equation. So this is, since we've linearized it, by definition, a linear equation for psi 1, right? So this thing is a linear equation for psi 1 of x, y, t, right? And what we want to know is whether that psi 1 is growing or decaying. And notice here that because my velocity is a function of y, right? So there is indeed rotationality to the flow, right? That if this has a velocity gradient, for instance, in y, du dy is non-trivial, so then I would have rotationality, right? So this is a rotational flow. There is a vorticity field in this flow. There's just no diffusion. So whatever the vorticity in the flow is, it's just being advected along. There's no diffusion of that vorticity, okay? We have this linear equation for psi 1, and now our question is, does psi 1 grow or decay with time? If it grows, so then we will say it's unstable. And if it decays, then we would say our system is stable, right? So is this little small perturbation, does it get worse and worse as it grow, and in which case the system is unstable? Or does it decay to 0, in which case we say the system is stable, the system goes back to its equilibrium? So this is the question that we want to analyze. Now, of course, you could analyze this for any psi 1, but if we make some assumptions about psi 1, we can simplify our analysis quite a bit. And if you assume that psi 1 can be represented as a superposition of normal modes, right? Just like in a Fourier analysis, you can represent any function as a superposition of sines and cosines. So we could say the same thing here, that I can represent psi 1 as a function of sines and cosines, or in complex variables, I don't say sines and cosines, but I say complex exponentials, right? So if I can represent psi 1 as a superposition of complex exponentials, which is true under certain assumptions, continuity and decay to infinity, etc. So if that's true, then I don't have to consider the general psi 1. I could just consider psi 1 as one of those modes, as one complex exponential. Because if I understand the solution for one complex exponential, it's a linear equation. I could just add a bunch of other complex exponentials and construct any solution I want. So if I can solve this, if I assume, right, I'm going to assume that psi 1 of x, y, t can be written as some shape function 5y times a complex exponential e to the I alpha x minus ct. So if this is the case, why do I choose this particular structure? Well, the complex exponential part, that's pretty straightforward. Here I have a traveling wave form, right? Here I have a wave number alpha. So we'll assume that the wave number alpha is real. Here I have C, that's my wave speed. We're going to assume that C is equal to a real part plus an imaginary part, right? And then we also have some sort of shape function or something that tells you how does the profile of this small perturbation vary with y. That, of course, can't be in the complex exponential. That has to be outside the exponential. Because if I look at my governing equation, I have all these u of y functions, right? The only y dependence in my governing equation is in this u term. So therefore, since my u term is not going to be some periodic function like a complex exponential, so I know that I'm going to have some non-periodic part also, where this is going to be somehow determined by my u of y, right? So this is essentially my sheet, the mode sheet. And then I have my traveling wave form. Traveling wave or normal mode. And once I wrote it this way, now I can analyze under what circumstances does this thing grow or decay. Well, all I have to do is look at my complex exponential, right? Here I have I alpha x, and then I have e to the I alpha, the minus sign. The C we said is CR plus I CI times T. So if I rewrite this again, I alpha x e to the negative I alpha CR T, then e to the negative I alpha I CI T, right? And then we see that, well, this is a complex variable. So this is a periodic oscillating function with like the x. This is complex also, right? So therefore, it's also oscillating with respect to time. But here I have these two i's, which are going to cancel. Two i's are going to be -1. So this quantity is going to be e to the alpha CI T. This is a real quantity, right? This is just a real exponential, which is either growing or decaying. These things are oscillating. These are periodic, right? Take the real, the imaginary parts. These are just oscillating functions. This last bit is actually changing the magnitude of the overall function. Under what circumstances does this decay? Well, if alpha CI is negative, so then it decays. If alpha CI is positive, so then it doesn't. Right? So then it's going to grow. So what's the condition for stability? Well, the condition for stability would be put a less than or equal to sign. This is our stability criteria. Alpha CI is less than or equal to 0. Well, if it's equal to 0, so then you just have oscillations, just pure oscillations. And if it's less than 0, then you have these oscillations multiplied by an exponential decay. This thing is going to 0, right? So this is our stability criteria. So our problem has become drastically simpler. We started with this equation that describes our perturbation, psi1. And we wanted to know, does psi1 grow or decay? As soon as we made the assumption that psi1 can be represented in this particular form, now the question of whether psi1 grows or decays is really much simpler. It's just a question of whether alpha CI is greater than or less than or equal to 0. Because if it's less than 0, then it's stable, it decays. If it's greater than 0, it's unstable, it grows. So our entire problem is we don't really even have to solve this equation. We don't need to know the exact form of psi1. All we need to know is what's the sum of alpha times psi I. That's the entire stability analysis, right? So we just need to figure out under what circumstances, if we want to demonstrate stability, under what circumstances is alpha psi I negative? That would be stability. Okay, so let's do that. In order to do that, of course, all we have to do is plug in our definition of psi1 into the governing equation and do some algebra.
doesn't this condition mean that the stability is dependent on the perturbation and not on the system?
No, why do you think that?
Because both alpha and C are parameters of the perturbation, not the system.
Right?
רוח ההורמון שונות על מערכת יציבה, רוח ההורמון אחרות היא לא יציבה. אבל זה לא פונקציה של המערכת, של ההפרעה.
Yeah. So which perturbations, what's the relationship between the wave numbers and the parameters of the system? Meaning you're right, that if you simply choose wave speeds that are negative, right, or wave numbers that are positive, so you have a stable system. But then you don't learn anything. But what we're going to find out is that this assumption of stability actually has implications on the system itself through a little bit of math, right? So we're going to see that yes, the particular wave numbers for stability or instability is just defined by this, right? That tells you right away. But there's actually a relationship between this particular assumption and the actual definition of the system. You'll see it. It's a little subtle, but not too hard. And of course, this is the entire stability course. So the problem that we're solving now, once you do this, you don't need to just take the stability course because this is the entire course. Okay, so substituting psi1 into this equation with the null node assumption. What do we get? Yeah, u minus y plus r over r times c times phi double prime plus 1 over y plus r phi prime minus alpha squared r squared over y plus r squared phi minus phi times u double prime u prime over y plus r minus u over y plus r squared equals 0. Now it's just a matter of doing some simplifications. So we'll do a little bit of renaming like we've done many times before. So we'll let our u, our velocity profile for the base flow, we'll let it equal y plus r over r times some function f. So instead of having everything in terms of u, we'll have a new velocity profile f. A new velocity profile, this will be a rescaled version of u. So it's just a new velocity profile, but it's going to make our math a little easier. So then once you do that, then we end up getting f minus c times the phi double prime 1 over y plus r phi prime alpha squared r squared y plus r squared phi minus phi f double prime 3 over r over y plus r f prime 0. Now we'll make another assumption. So we said that there is some curvature to the system. That's why we wrote everything in polar coordinates. But there's not too much curvature because we did a Cartesian, quasi-Cartesian analysis. So we now have to make a decision about how much curvature is too much. Right? So what we're going to assume is that our y is much less than r. In other words, we're going to assume that there's curvature, but that r is still pretty big. The radius of curvature is big enough that the curvature is slow curvature, slowly changing, nothing drastic, slowly changing. If that's the case, we have a bunch of these terms that look like y over 1 over y plus r squared over y plus r squared, r over y plus r. All of these things can be expanded by Taylor series if the assumption is that y is much less than r, right? In other words, the 1 over y plus r, if we assume that y is much less than r, so this becomes 1 over r minus y over r squared. And similarly for the other terms, the r squared over y plus r squared, this is 1 minus 2y over r plus higher order terms. So we can substitute these sorts of terms into our equation. And then, after we do that, then we're going to neglect terms that are of order 1 over r squared. So we're going to essentially write a series for any terms that have this 1 over r type dependence. We'll write a series for it. And then we're going to retain the terms that have 1 over r. So r has to be big enough so that 1 over r is significant, but 1 over r squared is insignificant. So again, we're just essentially it's just a truncation of this series. So we're going to allow for some curvature, but not too much. So we'll neglect terms that are 1 over r squared. And after we do that, we end up getting a substantially simpler equation. Still not quite simple enough. So then we end up getting an equation that looks like this: phi double prime plus 1 over r phi prime minus alpha squared 1 minus 2y over r phi minus f double prime plus 3 over r f prime f minus c phi equals 0. And now we're going to do one more substitution to simplify the math just a bit more. This time we're going to assume that that shape function, or mode shape function phi y, can be written as e to the negative y over 2r times a capital phi y. Just to make life even a bit easier, then I can simplify this more. Now I'll have capital phi double prime minus alpha squared 1 minus 2y over r capital phi minus this whole thing, f double prime 3 over r f prime f minus c capital phi equals 0. And now we're going to do one final trick in order to try to simplify this a bit. And that is, we're going to multiply this thing by the complex conjugate of phi. We'll call phi star. So if I multiply through by the complex conjugate, so all of these terms, so here I'm going to have complex conjugate. Here, the thing times the complex conjugate, well, that just becomes the thing squared. And here, the thing times the complex conjugate becomes a thing squared. And then we just have this term, which we have to deal with. So this term, we can write as the integral, right, of phi double prime phi dy. So imagine now I'm going to integrate this equation over some boundaries of the system. Y inner, y outer. And again, since we're talking about some sort of channel flow, so this might be the bottom wall of the system, this is the top wall of the system. Right? It doesn't really matter what it is. So eventually we're going to integrate this whole thing. But just let's deal with this equation first. So here we can use integration by parts. And this ends up being phi prime phi complex conjugate evaluated at these two limits minus the integral between the two limits of phi prime complex conjugate dy. And now we're going to make an assumption. Remember, phi represents the shape of the perturbation, right? Capital phi represents just like lowercase phi did. It's just a rescaling. So if this represents the shape of the perturbation, here we're asked to know what is the shape of the perturbation's complex conjugate and the derivative of the perturbation evaluated at the boundaries. Well, if we assume that these boundaries are the walls of our channel, so the perturbation would be 0 on the walls. There wouldn't be any perturbation, whether you want to argue by no penetration, no slip, or whether you just want to argue that the perturbation is somewhere in the flow, and by the time it gets to the wall, it decays spatially. So we're far enough away from wherever the perturbation occurred either way, we're going to assume there's no perturbation at the walls, and therefore this thing equals to 0. And then this quantity, well, thanks to the integration by parts, this is now the derivative of phi and the complex conjugate of the derivative of phi. So this is now just the derivative of phi squared. Why not? Okay, so let me write up the final form before we take our break. The actual equation that we're going to deal with. So we're taking this equation and we're going to do the integration between y I and y0. So we'll have an integration from y I to y0 of this whole thing. Y prime squared plus alpha squared 1 minus 2y over r 5 squared plus f double prime plus 3 over r f prime over f minus c squared y equals 0. And somehow, this equation is going to tell us everything we need to know. It seems like a very strange thing because all we're interested in is the stability, right? And we said the stability is when the alpha times CI is positive or negative. Now, this equation does indeed have alphas and C's in it. So we might be able to learn something about what the velocity field is supposed to look like. The velocity field is represented by F for certain types of stable or unstable flows, but it's not at all obvious how to do that, right? We know that C, the sign of this alpha times the imaginary part of C determines the stability, but what's the connection between alpha, the imaginary part of C, and the velocity field, which is F? So that's what we'll answer after the break.
How can we enforce no speed in neglected viscosity?
That's why I said that you have choices about how to justify this assumption. So you could pretend that for whatever reason, the perturbations die out on the wall, or you could just assume that, imagine that we're dealing with a flow in an infinite domain, no wall. So therefore, this is negative infinity, this is positive infinity. And just imagine that wherever the perturbation is in the center of the flow, spatially, if you perturb the flow here, that perturbation has to die out spatially. So if you go far enough away from the perturbation, it's gone.
Why can't we say that the imaginary, like the P, capital P is real?
Why can't you say it?
No, why don't we say it?
Why would it be?
How can it be imagined? How can it have an imaginary power? If it's like the amplitude.
It's not the amplitude, right? Remember, it's a complex function. Remember the psi 1.
Otherwise, no.
So here you have the traveling wave. This thing is not real, right? Because it has two pieces of information. This thing has an amplitude piece of information, but it also has a phase, right? And if I took I can rewrite this as the amplitude of y times e to the I. I don't know what I should use. I should use some other theta, I mean my phase.
A little bit.
Therefore, this is the phase angle that I would put in here, right? So at every y location, right, I have an amplitude, but I also have a phase. So if you imagine, think about what the mode shape looks like. you have a mode shape in Y. So you could have a mode shape looks like this. Let's say this is the center of the axis, right? My x, y. So this is right in the center point. So, and if you imagine that these are sort of levels, right? So you could imagine that I have levels like this, so that the magnitude information is all captured in the magnitude of y. But I can also have a phase in x. In other words, my mode shape might look like this. Right? And at each different y location, there's a phase offset. So the maximum of at this particular y location out of phase with this location by some amount. Right? So if I took this, it's out of phase by pi or whatever. Where is that phase information captured? Captured in here. So that's why I call it the shape. I didn't call it the amplitude. Right? I used the word shape to describe it. Because it describes the mode shape. But to describe the mode shape, you need two different things. You need to know the amplitude, which I can't really draw, but these are contours, so you can imagine the amplitude out, right? That's the strength of it. But you also need to know, is there any variation in this as you change y? Can you imagine some phase shift in x? That some things here are out of phase with things over there. And the answer is yes. That's why I prefer to refer to this as the shape, not the amplitude. Not the amplitude, it's a shape. It's amplitude and phase.
Because the total phase change of the perturbation changes both in time and in y location.
Well, so you can think of there's just one phase, right? So you can think of the phase as being with vector t or with x. Just your perspective. So if I drew this as x variation, right? But I can imagine that a fixed x and there could be a t variation also. Doesn't matter. It's a traveling wave, so it's going to be the same no matter which perspective you take. It's just your choice. But the important thing is that if it was only amplitude, then you would never be able to have something which varies in terms of its shape as y changes. It will all be the same, right? At every it might be stronger here and weaker here, but it's not going to be shifted this way or that way. So if you imagine that in a wall-bounded flow, if the general flow is in this direction, this is your wall-bounded flow, mode shapes tend to be inclined. And they end up looking like this. You end up getting a periodic chain of mode shapes. So this is what the mode shapes look like.
כל מיני helpings כאלה שהם נותנים ככה.
Yeah, so we'll talk a little bit about that next week. We'll talk about turbulence more. We'll talk about it. But the point here is that the only way this is true, this means that the amplitude up here is out of phase with the amplitude down here. This amplitude, as well, is sort of in phase with this. So you end up seeing the near wall region here is in phase with the far wall region of the previous node. So this is these are plus nodes, minus, plus, minus. Imagine it's like a sinusoid. So each sinusoid at each wall location could be out of phase with the next sinusoid. That's why this is important. This is a complex function, it's a shape function.
וזה כל הקורס של ציוות טירונות.
When we finish it, we have some things to do still. And solving this equation is still not so trivial, but this is the whole process. Take the equation, linearize, substitute, and then linearize and solve. That's it. That's all stability analysis. That's why I'm only using part of a lecture for it. Cover all of it briefly. If you had to figure these things out on your own, it would take decades because very smart people worked out what to do with these equations. But once they've already done the math, it's easy to reproduce it.
Neglect fusion in our example. Didn't we say a couple of lectures ago that both fusion and advection cannot balance the vorticity on their own, like we had this calculation?
There are lots of objections to this. So you have to take this one on a bit of faith that we can make this assumption. In reality, even what I said at the beginning, that diffusion always makes things more stable and advection makes things less stable, even that's not technically true.
Can you explain how diffusion makes things?
Well, diffusion, it wants to get rid of gradients, right? So if you imagine a perturbation, you imagine you have a nice, a nice uniform momentum profile, vorticity profile, and then you imagine you put a little perturbation into it. Well, this perturbation results in big gradients. So diffusion wants to get rid of those gradients. So it's going to try to move, if this is a high vorticity region, it's going to try to move some of this vorticity to the neighboring low vorticity regions. And then eventually it'll smooth out until eventually you get back to the flat situation. That's what diffusion should do. So therefore, diffusion shouldn't allow a perturbation to hang around. And if it can't hang around for very long, then it can't cause other perturbations in the flow because it gets spread out. Whereas advection takes this perturbation, and what does it do? It moves it around. So now it interacts with all the other flow and it causes other perturbations, right? So if the advection is much stronger than the diffusion, then you would expect this perturbation to perturb other parts of the flow as it gets moved around. And those other perturbations will perturb other parts of the flow. And pretty soon it's like a chain reaction and the whole flow becomes unstable, right? That's the basic idea. Again, it's not technically true. And so there are more complicated things going on. In fact, the diffusion can sometimes make the flow less stable and not more stable, but it's sort of beyond the scope of what we want to talk about. That's stuff that maybe Jakob gets into at the end of his course. But no, it's just the whole linear assumption that we're making here is not true, right? That the nonlinearities result in the fact that this diffusion can actually make things worse and not better. No, it's nothing to do with numerics. Pure just the physics, just the equations. You can see this. Okay, let's deal with this equation. So this is the equation that we got. Again, let's remind ourselves what we're trying to do. We're trying to understand the stability of a shear flow, right? Because we know that a shear flow is like our boundary layer is a shear flow. Now, the flow that we're studying is not exactly our boundary layer, because we said that our boundary layer is a flow that has diffusion, for instance, and it has a definite wall. And here we got rid of diffusion, we got rid of advection. But nevertheless, we're hoping that this is a shear flow, and we might be able to learn things about this, the stability of this shear flow that we can apply to things like the boundary. That's the basic idea. So what did we do? We took the momentum equations without diffusion. We substituted into the momentum equation base flow plus a small perturbation psi 1. We then linearized about this small perturbation, and we wrote the equation for just the perturbation dynamics. Then we said, let's assume that this perturbation behaves as a normal mode, in the sense that it has a shape, and it has an complex exponential traveling wave. And if we write the perturbation in that form, then it becomes very easy to determine whether the perturbation is growing or decaying, because it just depends on the wave number of the wave speed, for the imaginary part of the wave speed. And then we substituted that normal mode into our governing equation, and I claimed that by doing this, we're going to be able to relate our assumptions about the stability of the perturbation to the basic factors of the flow, in particular the profile of the base flow, which is encapsulated in this F variable. That's what I claimed. And this is the only equation that we have. So somehow we have to use this equation And if we look at this equation, you see that the whole integral is equal to 0, right? And is the equation real or complex? So this is real, right? This is real, real, real. This is real, but C is complex, right? So this term, particular here, this is our only complex term. So therefore, if this integral is equal to 0, well, it must be true that the real part and the imaginary part are both equal to 0. By definition, I should be able to rewrite this as two separate integrals. I should collect all the real parts in one integral, all the imaginary parts in the other integral, and both of those should be. And that's going to be the trick to simplifying this. So let's rewrite this term. It's f double prime plus 3 over r f prime over f minus c. We multiply this by f minus c complex conjugate. F minus c complex conjugate. Right? So f minus c times f minus c complex conjugate. So that's going to give you f minus c squared, right? And then you're going to have the f double prime plus 3 over r f prime. And then we just have f minus c complex conjugate. Right? Well, remember that c is equal to cr plus I ci. Right? So c complex conjugate is cr minus I ci. And if we do that, so we end up getting that this is f minus cr plus I ci. Now I've split this thing into a real part and an imaginary part. And since the only imaginary part in this whole integral is the one that has this thing next to it, so let me just I'll collect all the imaginary terms. There's a lot more real terms than imaginary terms, so it's better to start with the imaginary terms. There are fewer of them. So if I collect the imaginary terms, I end up having I times ci times this integral from I to yo, f double prime plus 3 over r f prime f minus c squared I squared dy equals 0. Now, this is a very interesting equation. Let's remind ourselves, for stability, so we said that ci times alpha had to be less than or equal to 0. So we can essentially ask at this point, under what circumstances, if the flow is unstable. So what does that mean? The flow is unstable. Ci is not equal to 0. Ci is positive if it's unstable. Assuming just for a second that alpha, this wave number, is some non-zero number, non-trivial, right? So therefore, for instability, just the opposite, right? For instability, alpha ci is greater than 0. Well, how many ways can I satisfy this equation? Well, ci could be equal to 0. Okay? Ci is equal to 0, so then we have a stable system. Or ci can be non-zero, and then this integral has to be 0. So if it's an unstable system, ci is not 0. Well, if ci is not 0, this integral has to be equal to 0. The only way to satisfy this is just a momentum. This integral has to be true. All we did was we took the momentum equation and integrate. This is just essentially a momentum integral equation. It was always true. But now we have a relationship between our assumptions about stability and things like the velocity profile, which is this after. So if the system is unstable, ci is not equal to 0, and therefore this integral must be equal to 0. So if it's unstable, so then the CI is not equal to 0, and therefore this integral must be equal to 0. Now, if this integral is equal to 0, what do I know about the stuff inside the integral?
They must change its sign. Like,
It has to change its sign. In particular, well, this thing, we said it's positive everywhere. This thing is positive everywhere. So in particular, it's just a numerator. I have my pen here. It's just a numerator. If this integral is equal to 0, and everything else in the integral is positive, it is just the magnitudes of these terms. So this thing has to change sign somewhere, right? Because when I integrate, I need at least some negative values and some positive values such that when I integrate over the whole function, I end up getting 0. So I need to have a change in sign. So if this is true, so if it's unstable, CI is not equal to 0, this has to be equal to 0. And that therefore we conclude that f prime plus 3 over r f prime equals 0 for some y. Has to change sign at some point. And this is our stability criteria. Right? This is essentially our stability criteria. This is what we've been looking for.
I'm speaking development.
You're saying this is which one are you saying it is?
Is it nice? Is it nice speak? It's official,
No,
but not
no,
necessary.
it's not. It's just you have the opposite. If this is true,
סליחה, כן, כן, זה necessary.
if this is true, right,
זה מה שהתכוונתי.
does that mean that it's unstable? No.
No, זה
Because-
שזה לא.
Why not?
כי גם זה יכול להיות ש-C היו שלילי. ואז
Exactly.
זה מה שהתכוונתי אליו.
Or 0. It can both be 0, right? CI can be 0 also. It can both be 0. So the fact that this is true, that this is a net, number one, the integral might also not be equal to 0 just because this is equal to 0, right? So this is really, this doesn't even prove that that's equal to 0. This is just a necessary condition for that to be equal to 0. So if this is true, it's not necessarily true that the integral is equal to 0. But moreover, if this is true, it could be that CI is also equal to 0. We just said that if it's unstable, then CI is not equal to 0. But it could be that it's stable, CI is equal to 0 or CI is negative, and this thing is still equal to 0. They could both be equal to 0, right? So it's a necessary condition, but not a sufficient condition, right? So this is a necessary condition or instability. Okay? Only necessary, not sufficient. Okay, but now let's examine this just a little bit more, right? Because f is sort of this awkward variable, right? We defined f to represent the velocity profile just to simplify the math, right? F was a rescaled velocity profile. But in reality, we like to think about things in terms of u. That's the actual velocity profile. So let's just rewrite this condition. Now that we got it, let's rewrite the condition back in terms of u. So this condition, we rewrite this. This comes out to r over y plus r times u double prime plus 1 over r u prime plus 1 over y plus r quantity cubed 2 u prime r plus y minus r plus 3y u. This has to be equal to 0, right? So this condition here in terms of f, that's equal to 0. This is what it comes out to in terms of u. Now, of course, in our earlier analysis, we already neglected terms that were 1 over r squared. And these terms here are going to involve r over r cubed. These are going to involve 1 over r squared terms. So we can neglect all of these. So if we do the same thing we did before, we neglect things that are order 1 over r squared. So then we're going to end up getting that u double prime plus 1 over r u prime equals 0. This is the condition. So this is our actual necessary condition for instability. Now, what happens if the wall is totally flat? Right, so if it's totally flat, R goes to infinity, right? We're allowing for slow variation, but if it's totally flat, so then R actually equal to infinity, in which case our condition is there has to be an inflection point, right? So the necessary criteria for instability is there has to be an inflection point in the velocity profile. And this is actually called Rayleigh's inflection point criteria. This is the official name for it. Now, we derived it in a much more general way. We derived it in a way that allows for curvature, right? But in this case, without any curvature, it's just a simple inflection point. Now, when we hear there's an inflection point in the velocity profile, what should this remind us of?
Separation.
Well, what about separation? Not quite separation, but it's something that we saw in our discussion of separation.
כן. אולי שמתחילה להיווצר רוטיסיות חיובית, ואז בהמשך תהיה סבבה.
The vorticity doesn't have to be positive, but what happens before the vorticity becomes positive?
יהיה אפס.
And even before that, when it's on the road to separation, so let's just draw. So we have our velocity profile. So we draw a velocity profile as an inflection point. Right? This is our velocity profile. Has an inflection point. Then I'll draw my vorticity. We'll do it in blue for the negative vorticity. So the vorticity is the derivative of the velocity. So if the second derivative of velocity is equal to 0, that means the first derivative of vorticity is 0. The first derivative of vorticity is 0 means there has to be a min or a max vorticity. So when we draw our vorticity profile, right, it ends up looking something like this. I didn't draw it, so it perfectly fits. Better job. So we have our vorticity. So we said that as the flow is on the road to separation, meaning once you start having that positive vortex sheet, so then you start producing positive vorticity that cancels some of the vorticity at the wall. Before the positive vortex sheet, the maximum vorticity is always at the wall. Every case we saw where there was a regular favorable pressure gradient, the vorticity maximum is always at the wall. It's only when you have an adverse pressure gradient, for instance, that you can start moving the maximum of vorticity away from it. So the definition that we have here for the Rayleigh's inflection point criteria, we should probably rename it. It probably shouldn't be Rayleigh's inflection point criteria. This is Rayleigh's inflection point criteria. What we should really translate this into, it should be the vorticity maximum or vorticity extremum. It should be a vorticity extremum criteria. Is the way we've been thinking about everything through the lens of vorticity. It turns out that what does an inflection point mean in the velocity profile? Nothing. It's just a mathematical description. Here it's concave up, here it's concave down, just math. When the vorticity has a maximum, that's going to have a physical meaning. Right? The maximum, the location of maximum vorticity actually has a physical meaning. We're going to explore what that physical meaning is. But that's the beauty of the vorticity perspective, is that Rayleigh's inflection point criteria is just a mathematical description, purely a result of all the math that we did. Okay, we know the second derivative. The velocity profile has to be 0 as a necessary condition for instability. But it turns out that when we think about that from a vorticity perspective, it actually has a physical meaning. Now, of course, if I'm claiming this is true, well, we better check to make sure in polar coordinates this more general form also works, right? So if I'm claiming that the vorticity maximum, right, is where the necessary condition is, so let's just calculate where our vorticity max is. So our vorticity polar coordinates is the r plus u theta over r. Again, we're not accounting any vorticity variation in theta direction. Where's the extremum in this with respect to r? So I'll take a derivative of this. That's where the maximum or the minimum of vorticity should be. That's equal to e squared u theta u squared plus 1 over r theta dr minus 1 over r squared u theta. This thing has to be 0. And then we can do the same Cartesian substitution, right? Our u theta becomes u, our y is r minus capital R, or vice versa. Capital R is y. So I can rewrite the vorticity max. This is the vorticity extremum equation. I'll rewrite that into our Cartesian coordinates. And this becomes e squared u uy squared plus 1 over y plus r y minus 1 over y plus r squared u equals 0. And then we do the same thing we did before. We write this as over 1 over r, right? Excluding, or we exclude the 1 over r squared terms. And if you do that, you end up getting e squared u y squared plus 1 over r y equals 0. Which is exactly the same as this expression, right? So we can see that the vorticity maximum, where the vorticity maximum occurs, where the vorticity with respect to r has its maximum to 0, in the Cartesian, quasi-Cartesian coordinate system, at the same level of approximation in terms of the curvature, gives us this expression, which is exactly the same expression that we derived from our integral. Okay, so just a double check, right? We just want to make sure that, obviously for the flat plate, it's very easy. I can translate from an inflection point to a vorticity. I know how to do that in Cartesian form. But is it actually true with the curved surface also? Well, I just want to prove to you that it is true. That in a curved system, under the same assumptions, you get the exact same criteria that we had before. Okay, that is basically the basic criteria for our stability. So let's just write it down. And then we'll see if we can improve it just a bit. There is a way to improve it just slightly.
But what if you analyze flows that don't have surfaces, like waves?
Doesn't matter. This works all fine. Remember, we only did from yi to yo. So if you take it as negative infinity to positive infinity, you can do the analysis. This can give you this stability analysis for a wake also. So the only question is there an inflection point? An inflection point would be a necessary condition for the instability of the wake. You need to look and show that the wake actually has two different concavities. Okay, so the criteria that we have, which is, again, it's due to Rayleigh. It's also due to a guy named Tolman. Right, the criteria is essentially that if the flow is unstable, then there's either an inflection point or we'll say an extremum in vorticity. Then the base flow has an extremum in vorticity. Again, it's a statement that's a necessary condition. If the base flow has extremum vorticity, that doesn't prove that the flow is unstable. But if the flow is unstable, then the base flow definitely has an extremum in vorticity. Okay, now I said we can actually get a little bit more specific in terms of our stability criterion than this. Because if you think, we had this big equation, which was equal to 0, and we only used part of it. We only used the imaginary part. We never used the real part of the equation. What happens if we use the real part of the equation? There was a guy who thought this very same thought. He said, why are we throwing away the whole real part of the equation? Maybe we can learn something else. We had this wonderful trick to learn something from the imaginary part of the equation. So this guy named Fjortov So Fjordtoft said, let's try to learn something from the real part of the equation. So let's look at the real part of the equation. So if we write the real part of the equation again, so this is yi, yo squared plus alpha squared 1 minus 2y over r squared y equals, now we have the real part of the term that we dealt with last time, which is f minus c real times f double prime plus 3 over r f prime f minus c squared y squared dy. So this is the real part. And Fjordtoft said we can look at this and we can realize in the case where the flow is unstable, we actually know something already. So when it's unstable, so we know that part of this integral is actually already zero, right? So when it's unstable, we know that the part that has the 3 over r f prime f minus c squared dy, this part is already equal to 0, right? If it's unstable. Well, we can make use of this, right? Because if this is true, this is equal to 0. So we can use essentially what's the only trick in mathematics, which is adding 0, right? Multiplying by 1, I guess, is the neighboring trick. So you can either add 0 or multiply by 1. So let's look at this term. If we add 0 to it, adding 0 to this side equation allows us to add this thing. But it also allows us to add anything that's multiplied by this thing. So he said, let's multiply this by something very tricky. Let's multiply this thing by the quantity CR minus F, evaluate at the location where this thing is equal to 0. And we'll call that YS. Right? So YS is where this F double prime plus 3 over R F prime equals 0. That'll be the location. We said it had to be true for some Y. Let's call that YS, right? In other words, if I put YS in here, that's when it's true. So it's just a number, right? So f of YS is just a number. YS is just a number somewhere in this domain between YI and YO, okay? So just like this thing was equal to 0 for instability, this is obviously also equal to 0, right? For instability. And because this whole thing is equal to 0, I can add this thing to this thing without changing anything. But of course, when I add this thing to that, I'm going to be able to do some simplifications. So let me do that. So I'll add 0 to that, to the equation of the real part. And then just do a little bit of algebra to simplify it. And we're going to get the following. Negative yi, yo, y prime squared plus the alpha squared 1 minus 2y over r y squared dy equals integral yi, yo. Now I have f of y minus f of ys. Then I have the same thing I had before, which is the f double prime plus c over r f prime, whole thing in the denominator, f minus c squared y squared dy. Now, the left side of this equation, this is positive, positive. Y is always less than r. That's positive, that's positive. The whole integral is positive. The minus sign out front. So this whole thing is negative. This whole thing is negative, so therefore this whole thing has to be negative. Now, if this whole thing is negative, what has to be true? Well, this part's positive, this part's positive. So for this whole thing to be negative, we have the exact sort of the same sort of analysis that we did here. If this thing's going to be negative, so the numerator has to be negative somewhere. Okay? There has to be at least some location where this numerator, I'll circle it in blue again. So this thing has to be negative if the whole integral is going to be negative. It has to be negative somewhere. Right? If it was positive everywhere, then there's no way for this integral to be negative. There has to be at least some location where this thing is negative. So now we have a new criteria, right? So that for instability, now we have a criteria that f y minus f ys times this thing, f double prime plus 3 over r f prime, that has to be negative for some y. And this is an additional criteria on top of our previous criteria. The previous criteria was just that this thing had to be equal to 0 for some y. Of course, we know that's equal to 0 for some y. Which y? Because it's ys. Right? But in addition to this thing being equal to 0 at some ys, there has to be another location where this thing is negative. And this is Fjortoft's criteria. Again, he figured this out just from using the exact same analysis that Tolman did, but instead of considering the imaginary part of that equation, he said, let's look at the real part of the equation and we get this additional criteria. And now the question is there any difference between them? Meaning, are there flows that are satisfying the necessary condition for instability for Tolman, but not for Fjortoft? Is there actually a factual difference between these two? So we need to draw some pictures in order to consider a bunch of different flows. So let me just sketch some flows, and then we can apply the different criteria to them and see which ones we think satisfy the necessary condition for instability and which ones don't. So I have 6 flows that I want to draw up. So
After this term, does this criteria looks like in terms of velocity u?
I'm going to draw.
How wrote Tolman's criteria?
Oh, well, it's easy. R goes to infinity. So that's the velocity version. So let me just, so everyone can see at home. So if you just take the limit, that's all it goes to infinity for the flat case. So this is the flat case. That's the criteria. Okay. Now let me draw some flows here. So we have we're going to draw vorticity profiles and velocity profiles. See both. So we'll draw a velocity profile that's concave down everywhere. And if it's concave down everywhere, so therefore the vorticity, the velocity is increasing with y, therefore the vorticity is negative. And since it's concave down, so therefore the vorticity has to be increasing. So this is our vorticity profile. And then we could do the opposite. We could have concave up. And again, notice I'm not really worrying about applying a no-slip condition at the wall or anything. It doesn't matter. We just have some arbitrary boundaries. I still have an increasing velocity profile, so the vorticity is still negative, but now the concavity is switched. So now the vorticity is going to be going the opposite direction. Then we could consider a case where there's an inflection point. So we could consider where it's concave down and then concave up. There's our inflection point. So if there's an inflection point, of course, it's still increasing, the velocity is still increasing with y, so the vorticity is still negative. But now you have where it's concave down, so you have this increasing vorticity, and where it's concave down, you have the decreasing vorticity. So you end up having a vorticity profile that has a vorticity extremum that corresponds to the inflection point. Then we could, of course, flip this. We can make it so that it's concave down and then concave up. Then it's going to be exactly the same, but this time we're going to have a vorticity profile that looks like this. And then we could have just two last ones just for fun. What happens if we switch the velocity profile direction altogether? So we can have it so that it's concave up and then concave down. So now our vorticity is no longer negative. Now the velocity is decreasing with y. Our vorticity, therefore, is going to be the opposite sign, but here it's going to look like this. And then, of course, we can do the opposite. Right? We can have it concave down and then concave up. Inflection point. Velocity still decreasing with y, and therefore positive vorticity with an inflection point. So these are the profiles that we can consider. So all we have to do now is check the criteria. Well, the first two are pretty easy, right? Because the first two, we don't have an inflection point. So if there's no inflection point, you don't have to go to Fjordtoft's more complicated criteria. We haven't even satisfied the Tolman or Rayleigh criteria. So these two don't satisfy either of them, right? So they don't satisfy either criteria, no inflection point. All the rest of them have an inflection point, right? So all the rest of them satisfy the Rayleigh criteria. So I'll put an R for the Rayleigh criteria. They all satisfy the Rayleigh criteria because they all have an inflection point. And Rayleigh said that's all you need. One point where there's an inflection point in the velocity, or from our perspective, a min or a max in the vorticity. So here's a min or a max in the vorticity here, here, and here. So all of those satisfy the necessary requirement for instability from Rayleigh/Tolman. Now we just have the Fjordtoft criteria. So in the Fjordtoft criteria, we need to check whether this quantity, uy minus, I'll write it over here on this board. So uy minus uys times u double prime, whether that is negative or not. So we just need to label these things. So here, this region, this is concave up, right? So this is u double prime is positive. This is u double prime is negative here. Here we have u double prime negative, u double prime positive, u double prime negative, u double prime positive, positive, negative. Right, just labeling the curvature, right? So now we need to ask ourselves, is there a location, right, where the u double prime times this subtraction is negative? So if I take a point with a different color, if I take a point here, for instance, so here, well, the u here compared to the ys, well, that's the point where the inflection point is. So here, u minus uy of s, that's a positive quantity. The velocity is higher here than it is there. So that's positive, and u double prime is positive because it's concave up. So it's positive times a positive. It's not negative, right? Same with, okay, if I chose a point here. If I chose a point here, my u minus u prime, that's negative, right? Because the velocity here is lower than my inflection velocity. That's negative, but of course it's concave down, so u double prime is also negative. So both of those, negative times negative, is also positive. So this one, it doesn't work for the Fjordtoft criterion. So this is not considered unstable or doesn't satisfy the necessary condition for instability for the Fjordtoft criteria, only for Rayleigh. So Rayleigh would have said, you sure, this could be an unstable flow. And Fjordtoft would say, no, it doesn't satisfy the necessary condition for instability. Go to the next one, right? Here, once again, we choose a point. This point, this velocity minus the velocity of the inflection point, that's positive. Here, the u double prime is negative. Now it's a positive times a negative. This satisfies the Fjordtoft criterion. And once we found one point, that's it. We don't have to check anywhere else. So this one satisfies Rayleigh and Fjordcroft. Same with this one. We go here. Here's a point. U minus uy. Here it's negative. U double prime is negative. Negative times a negative doesn't work. This does not satisfy Fjordcroft, only Rayleigh. And then the final one. U minus the uys, it's negative, but this is concave up, so U double prime is positive, negative times a positive is negative. This satisfies the Fjordcroft criterion. So the only ones that satisfy the Fjordcroft criteria are these two, right? And therefore, we can change our requirement before. It's not enough to have an extremum in vorticity, right? Because these two have extremum in vorticity. It's not enough. There has to be a certain sign or a certain type of extremum. If your vorticity is negative, like in this case, it has to be a minimum in vorticity. If your vorticity is positive, like in this case, it has to be a maximum in vorticity. But you can't have a minimum in vorticity when it's positive, and you can't have a maximum in vorticity when it's negative. So our new stability criteria, right, is that if the flow is unstable, then if the vorticity is negative, then there must be a min in vorticity. Or if the vorticity is positive, then there must be a max in vorticity. That's our new refined criteria. So this is a little more sophisticated than the basic stability analysis that Tolman did, but it all came from the same equation. It turns out that even though we said this is only a necessary criteria, it turns out it's actually a sufficient criteria. It's hard to prove, which is why we're not going to do it, but Tolman actually proved this, at least for certain types of flows. So if this velocity profile, U of y, if it's symmetric in a channel flow, so if you have a channel flow and it's symmetric, or in a boundary layer flow, if it's monotonically increasing, so you're only increasing velocity profile everywhere, if you satisfy either of those criteria, which are pretty easy to satisfy, most flows you can imagine are going to satisfy them. So if it's a symmetric channel flow or a monotonically increasing boundary layer flow, either of those cases, it turns out that the Tolman's criteria, at least, the U double prime inflection point criteria, is a sufficient condition for instability. Again, proving it is actually quite complicated. This was already sort of complicated enough to do all these integral tricks in order to prove this. So to prove that it's a sufficient condition is even more complicated, but it's true that it's a sufficient condition in a variety of cases. So this is, as I said, all the basics of stability analysis, the whole stability analysis course. But this is not what we're trying to do, because what we want to do is say something about what does this min or max of vorticity mean? Meaning it's one thing to say, okay, well, so the stability depends on the inflection point, but it has no physical meaning. And even saying, well, it depends on the min or max of the vorticity. But if that has no physical meaning, why should a flow with a maximum of vorticity be more unstable than a flow without a maximum vorticity? What is it about the presence of a maximum in vorticity that tends to cause a flow to be unstable? This is sort of the fundamental question that we want to answer. And this is a much more interesting question in my mind than just the mathematical formula. Deriving this formula is fine, but what we really want to know is physically, what is it about the vorticity and the way the vorticity behaves in the flow that means that when there's a maximum of vorticity or a minimum of vorticity, that for some reason perturbations can grow in such a case. But if you don't have a max or a min, then perturbations don't grow, they decay, right? It seems like it's a very strange thing. What's the relationship between the max or min of vorticity and whether a small perturbation in vorticity grows? So we don't have time, and I don't really want to start it this week, but the last thing that we're going to do in terms of our stability analysis, we'll do first thing next week, which is we'll take a flow very much like this in a little channel, and we'll put a small perturbation of vorticity in the flow. Now, what happens when you put a small perturbation of vorticity? Well, we know that, that any vorticity induces velocity changes, right? So if I put a little vorticity in a flow where it wasn't before, it's going to induce a little more velocity change than the natural vorticity in the flow. So the vorticity, putting vorticity in the flow is going to cause the velocity around it to change. The velocity, of course, when that changes, what does it change? It's going to result in changing the vorticity field overall, right? So you're going to end up getting a change in the vorticity field around it. And then when that vorticity field gets changed, that's going to induce a velocity back at the perturbation itself. So you have this sort of closed loop that you put a small perturbation of vorticity into a flow, it's going to affect the velocity field. The velocity field is going to affect the overall vorticity field. The overall vorticity field is going to therefore affect the perturbation. So you have this feedback loop. And what we're going to look at next week is what happens in this feedback loop, because something very special happens. Depending on whether you have a maximum or minimum vorticity, that feedback loop behaves very differently. And the question is, in that feedback loop, how does that feedback loop affect the ability of that small perturbation to grow or decay? And we're going to see that the ability of that perturbation to grow or decay depends on this feedback loop, and it depends on the distribution of vorticity. So therefore, we're going to show next week that it's not just a purely mathematical statement that there has to be a min or a max of vorticity, but in reality, the min or max of vorticity tells you something about physically what happens to a small perturbation in a flow. We're going to see how that happens. So that's the analysis we'll do next week. And then after we do that, that'll finish everything about stability, and then we'll start talking about turbulent boundary layers and analyzing them. So that's it for this week.
Does it concern that these vorticity profiles do not look stable?
What do you mean?
The derivatives, הפרופילים האלה לא נראים יציבים. הנגזרות פונות החוצה מהנקודה של הקיצון, לא לתוכה.
Which one are you referring to here?
לאלה שאמרנו שהן באמת לא יציבות. לעליון.
These are the ones that are stable.
לא, ללא יציבות. לימני העליון ולימני התחתון. ושניהם בנקודת קיצון, הנגזרות פונות החוצה מהנקודת קיצון. אז אני שואל אם זה קשור לזה שהסיבה שהם לא יציבים.
Not directly. No, it's not as simple as that, unfortunately. You could have the profile itself. Remember, this is the mean profile, right? This doesn't tell you anything about a perturbation. The question is, if you add a little perturbation to this, right? Or to this one, or any of these, you add a little perturbation to the profile. What happens to that perturbation? And for some reason, the perturbation in this case gets much, much worse. It grows and grows and grows. And yet, in this case, if you add a little perturbation, it's going to get smoothed out, right? So that's the question. So the question is not about the base profile itself. We're accepting the base profile, right? We're accepting that there is a base profile, whatever it is. We're not questioning the base profile. We're questioning, how does the base profile affect the ability of a small perturbation to grow or decay? That's a much, it's sort of a more subtle question. So yeah, it's nothing to do with the base profile. So you can look at the base profile and say, well, doesn't this look like it wants to diffuse away? And the answer is sure it does. But in a boundary layer also, the vorticity wants to diffuse away. When you look at the boundary layer, what does the vorticity profile look like? It looks like this. Doesn't it want to diffuse away? Sure it does. What prevents it from diffusing away? Advection. It's being advected. So it is diffusing away. It's diffusing away, but it's being advected much faster. And as it diffuses away, that's why the boundary layer is growing. The boundary layer growth is the diffusion of vorticity. But it doesn't diffuse away all of a sudden, it diffuses away while it's being infected. And that's why you have a boundary layer that ends up growing so slowly, right? Because this is the diffusion of vorticity and the advection of vorticity. And the advection happens to be much faster than the diffusion. So then you end up seeing a boundary layer growth. So this one also, you'd say, well, shouldn't it just diffuse? Yeah, it should, and it does. It does diffuse. And this one also, will it diffuse? Yes, it will. This would diffuse. Imagine this is like a jet or something, right? So you have high gradients in the center and low gradients at the outside. So you have high vorticity in the center. What happens to a jet? It spreads out. It's going to spread. Yeah, that's no problem. That doesn't tell you anything about the stability of it, though. Whether it diffuses and how fast it diffuses, that has to do with the relative advection to diffusion. That has to do with the Reynolds number. And that's fine. So these are going to spread, the vorticity will spread in different ways, right? This might be two different plates, right? You can imagine plates that are moving, right? And you could have high vorticity at the edges and low vorticity in the center, and it's going to diffuse. So the diffusion of the vorticity, how the mean profile, the base profile, the profile that's associated with the psi naught, what happens to that? We already studied that. That's just the laminar base case. And it diffuses and it advects, does everything. What we want to know is the psi 1. The small, when you perturb it. And that's the mystery, right? What in the world is the connection between a perturbation and a maximum or a minimum in the base profile? It seems like there's no physical connection at all, right? Like, what in the world does it have to do with the other? That's the weird part. That's the really strange part. How could a minimum in the base profile affect the perturbation? Why do perturbations grow in this one and not in that one? So that's what we're going to develop a physical model for to explain, because that's what they never explain in the stability class. They derive this expression, but they never explain physically why should this be true? Why should it depend on it? What is special about a mean base profile that has an extremum that's not true when it doesn't have an extremum? And how does that affect so small perturbation? And that's what that feedback loop is going to be about, which we'll model next week. Yeah, I know. Only because you CC the dean. Otherwise, they wouldn't have.